Okay. Hello, no one. Good. So the topic today is generalized least squares. And that's short for generalized least squares estimation of GLM parameters. And the outline today is that we first do a quick review of where we are with the estimation and distribution theory of the GLM under spherical error covariances. Then we're going to discuss the motivation to go from spherical error covariance matrices to non-spherical error covariance matrices. And then we discuss the GLS, so the generalized least squares beta parameter estimator. So this bit of theory is fairly straightforward, so I suggest we just continue without a break until we are finished with the entire content. So let's first review the formulation, estimation, and distribution theory of the GLM under standard assumptions. So of course we remember by now that the GLM in probabilistic form can be seen as a multivariate Gaussian distribution over some data vector y with expectation parameter given by a design matrix times effect size beta parameter and a covariance matrix parameter of this multivariate Gaussian corresponding under basic assumptions to the product of the identity matrix, the n by n identity matrix with a positive variance parameter. So remember that this is n-dimensional, this is n times p-dimensional, beta is p-dimensional, sigma square is larger than 0. And we've, of course, repeatedly seen that this corresponds to this structural form where the errors are normally distributed, centered on 0, and with spherical covariance matrix corresponding to identically and independently, or independently and identically distributed error terms. Yeah? So the assumption is that the EI for I to 1 to n are ID. Now, to estimate parameters, we have seen that by means of ordinary least squares or maximum likelihood, we can estimate the parameters as follows. For beta, we have the ordinary least squares estimator given as a function of the design matrix and the data. And for the variance parameter, we've seen that we have an unbiased estimator of the variance parameter given in terms of the data, the ordinary square estimate for the beta parameters and the design matrix. Resulting from the residual errors here, squared. Now, last time we've seen that from a frequentist perspective, the beta parameter estimator has a distribution, and this distribution is given by a p-variate normal distribution, which has as its expectation parameter the true but unknown value of the beta parameter, and as its covariance matrix the product of the design matrix with itself and the inverse of that multiplied by the error variance. And we've also seen that the variance parameter estimate in a rescaled version, namely multiplied by n minus p and divided by the true but unknown sigma or variance parameter, is distributed according to a chi-square distribution with n minus p degrees of freedom. And then finally what we looked at was the t-statistic, which for a given contrast weight vector merges the beta and variance parameter estimators following way. So in the numerator of the t-statistic we have the contrast weight vector CRP, which one can define as desired. We have the contrast weight vector times the beta parameter estimate minus the contrast weight vector times the true but unknown beta parameter, which ensures that the t-statistic is always centered on 0. And in the denominator we have the variance parameter estimator times the contrast weight vector times the inverse of the product of the design matrix with itself, times again the contrast weight vector, where we also notice that this here corresponds to the sigma square hat without the contrast weight vector, the sigma square hat times the inverse of the design matrix with itself corresponds to the covariance of the beta parameter. So essentially we have in the t-statistic we have a ratio between the value of a beta parameter estimate divided by an estimate of its variance. Well, so we get a high t-value if the variance of the beta parameter is estimated relatively low for a given fixed value of the beta hat parameter, and we get a low t-value if the variance of the beta parameters, which is of course a function of the error variance, is high. And then we've of course also seen that the t-statistic is distributed according to a t-distribution with n minus p degrees of freedom. So that's basically in a couple of equations the entire GLM formulation, estimation and distribution theory. So if one is clear about this, then one is clear about a lot of things. So just as a side note, so this is model formulation here. This is model estimation. And then of course with the t-statistic we can do model slash parameter. In this case it's more parameter evaluation. Entire model evaluation, but it's in the evaluation stage. So that's essentially it, but most importantly, all of this is under the assumption of Iid errors, which are embedded in the spherical covariance matrix. Good. So all of this holds, so these distributional properties, especially the distributional property of the t-statistics, holds if the errors are assumed to be independent and identically distributed. And the step that we are taking then today is to relax this assumption, to go from independent and identically distributed errors to correlated error terms. And the first question is why we would want to do something like that. And to this end, we now look at the motivation. And here we go to our application of interest, namely fMRI data. So remember, if you have here time, and here the MR signal of a given voxel, then what the GLM essentially does is that it comes up with a prediction of the expectation of the MR signal over time, which is encoded in the X beta, which is an n-dimensional vector. If you plot this over time, you get something like this, for example. Depending on the resolution, of course it's discrete, so I'm putting down some discrete points here. So this is the prediction, this is not observed data. It's more the formulation. Now, when we talked about independent and identically errors, thus far, what we always assumed is that for each time point, we sample an additional error to the deterministic prediction. So for example, we sample here this point, and then next we sample this point, for example here, this here, this, and so on. And if we zoom a little bit in and ask ourselves, what does that actually mean, that we assume independent and identical errors for all time points, we can understand this as follows. So let's say we zoom in here, and for this time point, which we call I, and for this time point j, which in this case is I plus 1, but it doesn't need to be, it can be any other time point than I, we look at the error distribution. So here we would have epsilon I, here we would have epsilon j. Now if you again think about the frequentist intuition of the GLM, we can sample observed, we can sample observed time series here, our y's, y being x beta plus epsilon, many times, which corresponds to sampling errors many times. And what we are interested in is the distribution of two time points over many of these repeated samples, which of course are hypothetical. We only have one observed data series in reality, but the model of course says that the epsilon are distributed, and hence we can imagine taking many samples. And for these many samples we only look at two time points now, at I and j. Now the Iid assumption means that if we sample a large value for EI, So for example, we sample this. Maybe I make it red because that's how it is above. We sample this here for EI. Then the probability to sample a large or a small value for EJ is equally large. So if we're now thinking about having sampled EI as a relative large value in this coordinate system, we may sample an EJ here, also a large value. But we may equally sample a low value. And this holds for all of the EI and EJ. So for example, if we have a small EI value sampled, then we have the same probability to have an low EJ or a high EJ. Of course, if you think about the normal distribution, these values that are fairly low and fairly large, if we center this whole thing on 0 here, are themselves not that likely, and what is more likely is actually to get something close to 0. So we get many more data points here, sorry, not data points, arrow points, and get less samples here. And of course this is just again representing the spherical error covariance matrix, which in analytical form we would put as a circle of isocontours for the Gaussian. Like this. Yeah, so that's the IID error case for 2 errors of our time series here. So that's about this here. Now, it turns out that if one actually does MR signaling and creates a model of the data that is based on the stimulus-induced variability. So for example, what we see above there, our observed bold response, like this, is purely due to the fact that we say there is a stimulus presented here. Yeah? So that's stimulus presentation. Now in addition to, maybe let me finish this. So here we have our discrete data points. So in addition to the stimulus-induced activity, in a biological system we of course have many other things going on. So for example, the human participant is breathing. Breathing changes the CO2 concentration in the blood, also in the brain, and hence also affects the bold signal. Now we assume that we don't measure how people are breathing, so we cannot make a deterministic prediction about these errors. About the CO2 concentration changes induced by breathing. However, we know that if people are breathing in addition to the stimulus-induced activity, then on certain time points during the post-stimulus response, the CO2 concentration will be a little bit higher, because people are basically getting ready to breathe again, meaning that on 2 time points following each other, the MR signal will be both higher than our prediction. So let's call this now I and J again. And now the important thing is that what we assume is that there exist these form of short-term correlations, so that neighboring errors have a higher probability to deviate in the same direction from the deterministic prediction than errors further apart. That doesn't mean they always need to be positive, it just means that errors that are close together in time have a higher probability to be correlated than errors further apart in time. So if we again look at just two of our EI and EJ, what I just said means that whenever we sample a high value for I, so for example here, then we have a higher probability to sample a high value for EJ than a low value. Yeah? And the same for low values of EJ. And roughly similar in the middle. So what this is of course referring to is a covariance matrix that predicts correlated errors that are close together in time, which if you would plot the joint PDF of two errors close together in time would look like this. Yeah, so we have a non-spherical covariation structure of two errors in time, which is induced here, this non-IID case, by unspecified systematic signal covariations close in time. Now it's very important to get clear about what this means. So if you have a model of these covariations, so if you can say, okay, people are breathing in here, so I can account for this breathing in the deterministic part, so in the X-beta part of my model, then of course the assumption that there are error correlations is not really required. Yeah. The thing is, it's not only the breathing, it's also the heartbeat, it can be motion artifacts. So the idea is that there are many things that can induce correlations in the error terms, not all of which can be recorded. However, that said, this serial error correlation business was dealt with in the 90s, early 2000s, when people actually didn't have the means to collect a lot of other physiological data with the scanner as they have now. So for example, now we can record the breathing with a breathing belt, or monitor O2 with an oximeter, and we can monitor the heartbeat with an ECG. So you now also often see that people, based on these physiological parameters, create regressors that they include in their GLN. And then, of course, modeling error correlations becomes somewhat obsolete. However, often it's still done to account for any form of residual correlation. Yeah. So it can't hurt. Of course, you can maybe describe things better if you put them into the model in terms of the deterministic prediction, so in the design matrix. But if worse comes to worse, the correlation structure of the errors is estimated as being spherical, so IID, and then you have lost nothing if allowing for the fact that you might have error serial correlations. Yeah. So that's serial correlations, error serial correlations, and its motivation from the fMRI perspective. And we will get back to this now when we, of course, when we first discussed the generalized square estimator, but then also the variance component estimation that, for example, happens in SPM together with Ramel estimation. So we will get back to that and talk about models for the error correlations again. Today, the only thing I want to achieve is to basically go from the scenario that we have a spherical covariance matrix to a scenario where we don't have a spherical covariance matrix, so where we have a matrix V, which is symmetric and positive definite, so that we have a proper variance parameter, but yeah, we don't talk about its details, and the most important thing is that it's not the identity matrix, so V is just not IN. Well, and we will get back to close our more specified and more specific error covariance matrix parameters soon. However, to get started with the whole thing, we now essentially assume that our error covariance matrix is not the identity matrix times sigma square, but a non-identity matrix, positive definite, and we look at the effect. So the first thing that happens if you have such a scenario is that, of course, this assumption of the GLM is violated. Yeah? So it just doesn't hold anymore, and hence there is no guarantee that specifically the estimator formulas or the distributional properties of these estimators hold. And this can be fairly straightforwardly visualized, and this is what I want to show you next when talking about the t distribution, because this is, of course, essentially what people are most interested in, because this is essentially the result of a study. So what we have here on the left side is a spherical covariance matrix for 10 data points. I think it's a simple linear regression design. 10 data points, and data was sampled from this GLM, and like we saw last time, the t distribution was evaluated, and its histogram was evaluated over these repeated hypothetical samples. In this case, these were real samples taken on a computer, of course. Histogram was evaluated and compared to the t distribution for 8 degrees of freedom, because it's 2 parameters in the simple linear regression design, so n minus 2 is 8 degrees of freedom. And we see that this fits, and so the distributional theory of the GLM holds. Now, in this case, we look at a covariance matrix that actually encodes some form of correlation in neighboring time points. So, for example, if you look here, 1 and 2, 1 is, of course, self-correlated, or basically representing its variance, but then in 1 and 2, and so 2 and 1 as well, also show non-zero correlation. And this holds for all of these time points. So, for example, here, say this, 6 and 5 and 6 and 7 are also somewhat correlated. Now, if we look at the t values that result from sampling this, and we compare it to the t distribution that is supposed to hold, in this case, we see the following. We see that we have definitely more high and very low t values than predicted by the density of the t distribution. Yeah? So we get samples t values here where the t distribution says the probability is actually quite low. So in reality, if we have something like this, we have a higher probability of observing something here than predicted by the model. So we increase our false positive risk if we use the t-distribution for statistical testing. Yeah. So essentially, the bottom line of this is if you have, in the presence of error correlations, because the actual distribution of the t-statistic doesn't follow the theoretical distribution of the t-statistic anymore, you increase your risk for false positives. So one way to view that is, of course, if you have error correlations, you have less independent data points, so you essentially reduce the number of data that you have compared to the theoretical amount of data that you have, which is given by the number of data points minus the number of parameters. And because you reduce this, you have less data, and hence you become overconfident in your results. This can be looked a little bit more closely. So, of course, this is at the level of the t-statistic, where all of the assumptions and the distributional properties of the GLM are already summarized. If one looks a little bit more closely to where things are going wrong, then this is also quite insightful. So we briefly now look at the non-spherical errors effect on beta parameter estimation. And to think about this, we first look at the expectation of the beta parameter estimate, which is of course given by the expectation of the formula for the beta parameter estimate, which then with the linearity of expectations can be rewritten as this, which then, because the expectation of y is of course the design matrix times the true but unknown parameter value, is better. So what we see in terms of the spherical error effect, there is none on the expectation of the beta parameter. So it's not that the beta parameter estimates get biased by the non-spherical errors. But what happens is that the covariance matrix of the beta parameter estimate changes. So you might remember that from the linear transformation theorem for Gaussian transformations, what happens here is that we need to transform the covariance matrix of the data by the transformation matrix, and then we get the, so let's call this beta hat, and this sigma y, then we get the covariance matrix of the beta parameters. So we did that last time. Now, if we start not from the spherical covariance matrix, but now from the non-spherical covariance matrix, the formula in the linear transformation theory for Gaussian distributions evaluates like this, and what we get is this statement. And last week we had here for V we had In, and then we ended up at this covariance matrix for the beta parameter estimator, but here we have V doesn't equal the In, so we definitely don't get there. Yeah, so that doesn't happen. So our covariance matrix, if we assume non-spherical errors, is not the covariance matrix that enters here, and hence the distribution of the beta parameter estimate, this one, is not as it is supposed to be in the case of spherical errors, which also then means that the t-statistic is definitely not guaranteed, as we've already seen in terms of simulations, according to a t-distribution, because this is based on this covariance matrix parameter. Yeah? So what do we have essentially as results of error serial correlations? First, our error covariance, let's maybe do it like this, the error covariance is not this. This is of course the basic thing, that the data are not IID. And then we have that the covariance of the beta estimate is not this, from which it then results that the t distribution, as we've already seen, is not distributed according to this. Yeah, so that doesn't hold. And I mean, it could go either way, but as we've seen, because we effectively reduce the data that we have compared to by means of error correlations compared to what we think, how much data we have, we increase our false positive risk. So these are the consequences if we have non-spherical data. So we have to somehow account for the fact in the estimation theory. Yeah. So if we have good reasons to believe that we don't have spherical errors, then we should not use simply our theory on our theoretical results that come out under spherical errors, but we should build in the fact that we have non-spherical errors. And this will be then, after all, the topic for the next hour to introduce the generalized least squares beta parameter. So let's have a brief break now. Okay, so based on this idea that if we have non-spherical error correlations or serial error correlations, then our standard distribution theory for the GLN does not work. The idea for the GLS beta parameter estimator is now to render the GLN such that we still can use the standard theory. Yeah? So let's call this the GLS beta parameter estimator. And the fundamental idea is that if we have a GLM with non-spherical error covariance, which we might write as this, then the distribution theory violated. The idea is that we transform this GLM to a GLM with the transform, so I'm putting a function here now on ZMAP. We will not see this, but the idea is that we transform that's also not quite correct, no. We actually transform the entire GLM. So we transform this whole thing, so maybe let's call that T as a transform, or let's call it F, because T sounds like a T statistic. So we apply some form of transform to this, such that the distribution theory is no longer violated. So that's the general idea of generalized least squares. And to make this more specific, let's have a look at the details. So what we assume is that we have our GLM, where as always these are n-dimensional things. This is n times p, this is p, and our epsilon is distributed according to a normal distribution, and now of course with non-spherical error sigma square v. Now we assume that we can transform this, namely by multiplying this whole thing with a matrix A, so that we get on both sides A times A x beta plus A epsilon, where A is actually a square matrix. Yeah. So for that, so A is a square matrix, a multiplication transform, or transform and the transform is times, or pre-multiply on both sides with a matrix A. So then we can write this as again a GLM, where we define these entities as follows. Y star is an n-dimensional thing, and Y star is of course defined as A times Y. X star is n times P, and X star is A times X, and epsilon still n-dimensional and defined as A times epsilon. Yeah. So note that we transformed here the data, the design matrix when we do this, and the error, but not the beta parameter. Yeah. So the beta parameter in this transformed GLM is still the original beta parameter. Well, so if you assume that this is here the true but unknown beta parameter, we multiply everything by a matrix A, we still have the true but unknown beta parameter in there. And we can of course, in this new GLM here, evaluate the ordinary least squares estimator for beta, which would be beta hat x star t x star minus 1 x star t y star, which is of course just given in terms of our multiples here as this. And is an estimate of original beta true but unknown. Yeah. So far we've just shown that maybe we transform a GLM and then we can estimate by multiplying everything with a matrix, and then if we estimate the beta parameter, we still get an estimate for the true but unknown beta parameter, which is good, so the transformation doesn't change the parameter that we are interested in estimating. Now, we haven't said anything about this form of the matrix A. And of course, we want to choose the matrix A in some way that the covariance matrix of this is not affected by the effect of the spherical error, of the non-spherical, of the zero correlations in the errors. And to achieve that, what one can do is to define A in such a way that it corresponds essentially to the square root of the matrix V. So to get started on this, assume that V can be written as K times KT for a matrix K, which is actually triangular. We don't really need to know that much about the matrix K, except that it has the following properties: that the transpose of its inverse is is the inverse of its transpose, and that we also can write V, the inverse of V, as K minus 1 T. K minus 1. Yeah? So essentially what we're finding here is a matrix K that you can view as the square root of V, of the matrix V, because if we multiply K with itself, then we get V back. And now we want to actually see what happens if we set our matrix A to the inverse of one of these vectors K. Yeah? And what then happens is that our transformed errors, our epsilon star, are actually spherically distributed. So in our transformed version of the GLM, in this one here, this transformed GLM, the errors are no longer non-spherically distributed and non-IID, but they are again spherically IID distributed. Why does that hold? Let's have a look. So essentially we need to transform the distribution of the original errors under the multiple K minus 1. And if you remember from the linear transformation theorem, we get that the transformed expectation parameter is the transformation matrix, so K minus 1 times the original parameter, which was 0n, so we have K minus 1, 0n, and the transformed covariance parameter is given by the transformation matrix times the original covariance matrix times the transpose of the transformation matrix. And of course this evaluates to 0n K minus 1, the sigma square we can take in front, and then our V, and this is of course the trick, our V is KT, and then here we have K to the power of minus 1t. We assume that this is the same as KT minus 1. So what we get is 0n sigma square In. Yeah? So the trick here was to use a transformation matrix A that we apply in or to our non-spherical GLM, to the case where we have a non-spherical error covariance matrix here, and then use the linear transformation theorem for Gaussian distributions to show that the errors of this transformed GLM are again spherically distributed. Now, so in brief, for what in our spherical, in our transformed GLM here, if we choose for A the inverse of this square root of V, we have epsilon star being distributed again IID. So we have again our standard assumption. Now, if we want to estimate the parameter in this transformed GLM, here this beta, then we of course need to apply our formula, which we've seen above, evaluates to AX T AX minus 1 AX T AY. Now we put in our K to the power of minus 1, which we assume is our A matrix for transformation. So we get this expression. And then with the properties of K, we get to K minus 1, K minus 1 xt, and here we get to xt K minus 1 T K minus 1 Y, and this is also the same as K minus 1. And this is also the same as there was a T missing, sorry. There needs to be a T, there needs to be a T, and now these terms are V minus 1. Because that's how we set it up. So we get our generalized squares estimator, which has this form, where you obviously see that the sandwiched multiplication here corrects for V not being equal to IN. Because if you have IN there, then you get back to our ordinary least squares estimator. And this should be a minus 1 here, and this is missing there. Yeah. So to write this up again, our beta hat GLS is defined as xt b minus 1 x to the power of minus 1 xt b minus 1 y. Yeah. So the generalized least squares beta estimator corresponds to a corrected version for the beta ordinary least squares estimator under non-spherical errors. And the correction affects the covariance matrix of this beta estimator. Yeah. Now the question is, of course, where do we get this V from? So how do we get this? And this is actually, if you want, beyond the scope of the course. In linear algebra, one can show that for a positive definite matrix V, which it has to be because it's a covariance matrix parameter, such a matrix K that fulfills these properties always exists and can always be computed based on a single value decomposition, something that we will discuss in the summer term, so we don't have to worry about it. Yeah, so we can always compute it. Now this is the so-called Generalized squares estimator. In fMRI, this is also used, but with a somewhat different emphasis. And this is the last thing that I want to discuss, namely the notion of data whitening. This is a term you find a lot in the fMRI literature. So here the idea is, again, we start from a GLM for which the error parameters are non-spherically distributed. Now again, we apply some transform. Such that the transformed errors call them epsilon star here, are normally distributed with spherical covariance matrix. So that for our transformed GLM, the standard GLM theory holds. And we can use t values in the t distribution to ask about the true but unknown beta parameter. Yeah? Now, the matrix that we use for this transformation is of course the same as previously. So what we use here is a whitening matrix, which we define as k minus 1. We call this the whitening matrix. And if we now set wy being wx beta plus e, then our w epsilon is distributed again to a normal with spherical error covariance matrix. And this is then referred to as the whitened GLM. And here the standard theory holds. Yeah. So this is the whitening approach that we hear in fMRI always about. Now, that is essentially it. So we discussed data whitening and we discussed the generalized square estimator. One thing that I haven't emphasized, but which was inherent in the whole thing, is that we actually know V. Yeah? So if we want to use this transformation here, we need to know V. So that's important here. need to know V, because otherwise we cannot compute its square root, so the K matrix, and we cannot apply this whole idea of data whitening. Now, what we have developed so far, if you remember our estimators, we developed estimators for beta hat and for the variance parameter, but we haven't really developed anything that would allow us to estimate this entire thing here. Yeah, so we always assume that's the identity matrix, so we only have to estimate this one parameter, and we can do it like this. But we haven't addressed the problem at all. If this is not the identity matrix, how can we estimate this matrix? Yeah? And also in what we did today, we assumed that V is known. If we know V, then we can apply all of this, and we can get to a transformed GLM where we can apply our standard GLM theory. So again here, this holds for known V, because V is KKT. So we either assume that we know V, or we have to estimate it. And of course, in fMRI we don't assume that we know V, but we estimate it. And this will be the topic for then the next 2 sessions before Christmas, namely questions of covariance matrix, which is the same thing in a way as covariance component estimation, and the way it's done in fMRI is using restricted maximum likelihood. So one can do covariance component estimation in the maximum likelihood setting, but because restricted maximum likelihood is a little bit better, fMRI is done and inherently linked to restricted maximum likelihood estimation. So these 2 topics, covariance component estimation and restricted maximum likelihood estimations, will be then the big 2 topics before the Christmas break. Yeah. So again, today we developed the generalized least squares estimator as the estimator for the beta parameter in a GLM with non-spherical error covariance. It accounts for the fact that the errors are serially correlated by sandwich multiplicating the inverse of the covariance matrix into it. That's the GLS beta estimator, and we can transform the entire GLM to a GLM with spherical errors by multiplying with this whitening matrix and then use the standard theory. This will be a theme and an essential step that will come up like in 2 weeks again, when after we discuss covariance component estimations and restricted maximum likelihood estimation, we will see how this is actually used in fMRI data, where the B matrix is essentially assumed to be known based on pooling its estimates over many voxels. Yeah, so we will get back to this. So today is kind of the first exposure, and we will go back into it. Good. Thank you. That was it. Good. So then in the next half an hour, because I don't think we need more, and also we are a little bit late, we will now, after this motivation of Ramel, get started on where we actually apply it to and what the basic foundations of it actually are. And So that the main thing that we are now dealing with can be framed as covariance component estimation, and as I said earlier, in principle, of course, you can also do a covariance component estimation using maximum likelihood. There's actually a very good book by Searle, which is called Variance Components, that explains the whole thing in a much more comprehensive way. Components. But in neuroimaging, covariance components estimation is always done using Ramel. Yeah? So one can do covariance component estimation using maximum likelihood or restricted maximum likelihood. Because we are doing neuroimaging, and we will focus on doing covariance component estimation with Ramel. Yeah? So then, of course, the first question is, what does this mean in terms of covariance? What are covariance components, and what is the model that we are dealing with? And that's in some sense similar to last week when we discussed generalized least squares. So the main point here again is that we are dealing with a GLM, so with our standard GLM as always. However, the errors are distributed now not in a spherical manner, but with some non-spherical covariant matrix parameter, or covariance matrix V lambda. So remember last week we just had some V where we said V is not, sorry, not the estimate. V is not the spherical matrix, so it's not just a diagonal matrix with the variance parameter on the diagonal, but it's different. It's still positive definite, of course, because it's a covariance matrix, but we didn't specify anything more specific. And this week, and the way it's done in covariance component estimation in neuroimaging, we impose some more structure. So this V lambda means something which we will look at in a second. So this is of course the same thing as saying, like previously, that our data is distributed according to a multivariate normal distribution with expectation parameter x beta and covariance matrix V lambda. And just for completeness, everything else is of course as previously. We have n-dimensional data points, we have an n times p-dimensional design matrix, and we have a p-dimensional beta parameter vector. And the question is now, what is V lambda? So V lambda is given by the sum of k covariance component parameters times covariance components basis matrices. That's how I call these things. Let me first write it down and then I tell you in detail what these are. So the important thing is, of course, now the covariance matrix parameter of the GLM that we're looking at. And of course it needs to be positive definite, so it just needs to be a proper covariance matrix. It needs to be symmetric and yeah, positive definite, so that it can work as a covariance matrix parameter in the multivariate Gaussian. And the structure that is then imposed here, and is always imposed in neuroimaging, is this sum of scalar parameters lambda I times covariance matrix basis functions, or covariance basis matrices, I think that's how I call them. Covariance basis matrices, that's how I call them. So these are matrices, so each Qi is one matrix, and covariance component parameters. So what happens here is that we have covariance component parameters, these lambdas, lambda 1, lambda 2, up to lambda k, and we have covariance basis matrices Q1, Q2, and so on. For I being 1, lambda 1, and Q1, we are actually back to the case of a spherical setting. So the first covariance component basis matrix, or the covariance basis matrix Q1, is always the identity matrix. Yeah? So let's look at a first example for V lambda. So if we example 1, if we define k to be 1, and we define lambda 1 to be sigma square, then of course this formula V lambda says that we only have I from 1 to 1, lambda 1, Q1, and because Q1 is always the identity matrix, we just have sigma square IN. So our GLM, our spherical GLM, as we had it all the time, is just a special case of this more general GLM with this covariance component structure. And to give you the most important example also right now, because this is the one that is always estimated in and formulated in fMRI, we let k be 2. Yeah, so in fMRI it's not like there are 10 covariance components and basis matrices and component parameters, but there are 2. Yeah, instead of 1 in the spherical setting, there are 2. But this requires then this whole business of covariance component estimation. Here the matrix Q2, which we need to specify, because Q1 is always already specified in terms of the identity matrix, takes this form. So it's based on the product of a matrix set with itself, where the matrix set is defined as follows. I is larger than j, and 0 if I smaller than j. So basically this what this yields here, so this thing here is the negative part of the exponential function. So if you think about the exponential function, and we have 0 here, then we are talking about this bit here of the exponential function, which goes down the further away or the larger away I is from j, and it's 0 elsewhere. The question why this is of interest to fMRI, and also kind of an intuitive understanding of this, we will do once we talk about random processes and this AR1 white noise business. So this matrix that is behind this relates to this thing in the SPM or the fMRI model formulation AR1 white noise process. It's not trivial at all how this matrix, what this has to do with the autoregressive process. So we will take our time to discuss this after Christmas. So that's something, so where this matrix is coming from, this is something for 2020, not right now. But right now we have the second example here, which then is our lambda 1 times In plus lambda 2 Q2, and our Q2 matrix is formulated like this. So this is the SPM also FSL covariance matrix. Yeah. So the main point is here that it's not in fMRI, it's not just this, but there is an additional thing that induces actually the temporal error correlations that we discussed at the beginning of last week. So if you watch the video again, we discussed error correlations, and these error correlations are modeled using this matrix here. And how exactly this is done and why it comes down to this exponential decay, this we can only really understand if we know what stochastic processes are. And because we need stochastic processes for random fields, we will discuss this only after Christmas. But for the moment, the main point is that we are now not interested in GLMs only anymore where we have a spherical covariance matrix, but we are interested in this linear combination of covariance basis matrices with covariance component parameters. And one other thing that is very important that I haven't said yet, the QE are assumed to be known. Yeah. So for example, this matrix here that we use in fMRI, this is a fixed matrix that we know, but the lambda I, these are the parameters, and sometimes these are also only referred to as the covariance components. They are unknown. Yeah? So when talking about estimating the model, we are not only estimating now the beta parameter and the variance parameter, but we're estimating the beta parameter and all the lambda i's. And then we can, of course, summarize the lambda i's in a vector lambda 1 to lambda k. So these are also now free parameters of the GLM that we are interested in. Yeah. So this is the model formulation for covariance component estimation. Again, the most important thing is that we now have a sum of covariance components. The sum is given by a linear combination of these lambda things times the basis matrices. The basis matrices we know. In fMRI, there's only one basis matrix in addition to the identity matrix. Namely this Q matrix that is formed by multiplying a this Z matrix with itself, and this Z matrix being filled in using an exponential decay. We will look at that in detail in January, but that's it. Yeah. So the whole covariance component estimation business is really just about this thing here, and in addition to what we assumed last week, that it's non-spherical, it's now based on this linear combination here. So that's the question.
Yeah, why is it only one? additional covariance matrix.
Yeah.
Also, I mean, it could be, for example, like get ready to breathe again, right? Like in the example last week.
Yeah. So you watched the video.
Yeah, and it's like, is it? But you can, I can mention multiple sources. So that's
yeah. So the thing with the respiration last week. So one thing is so again, this is about modeling the error serial correlations. If you know sources of variations like breathing, then of course you can put them into the design matrix. So the question is now where you put variability in the data Y. Do you put it and model it in the design matrix, or do you model it in the covariance matrix? And in general, the idea would be everything that you really know and can describe, you put into the design matrix. Everything that is left, where you have no precise knowledge about, but you think that this might induce deviations from independence in the errors, you put into the covariance matrix, and then this exponential decay here is kind of the very general model for error serial correlations. So two errors being correlated, and the further away they are in time, the less they are correlated. You can, and this is actually also happening, you can also impose more structure in the covariance component. So for example, if you apply this in some form of repeated measures, ANOVA, then you could put into error correlations that relate to participants. And of course, you can also come up with more complex error correlation models that are not based on something deterministic that you measure, but somehow motivated by something. So I think basically trying to put everything that you know into the design matrix, and then allowing for some serial correlation that I mean, what you could think of course, different forms of decay, so that you have a fast decay and a slow decay, things like that. Right now, actually, it's always a fixed decay of the serial correlations over time that is put in. So one could do more, but things like breathing, so deterministic things that you measure, you would rather put into the design matrix. Yeah. Good. Any other questions about this? Good. So then to summarize this, we can very quickly, you can of course just write the covariance component GLM as P beta lambda over the data is a multivariate normal with X beta and V lambda. The V lambda is lambda E Q E. Yeah, so that's if you don't go into details about it, you can briefly formulate it like this. And now if K of course is larger than 1, so if we are not only dealing with, maybe this, we should still specify that Q1 is always the identity. If we have K being 2, then we have one more parameter to estimate. And lambda 1 also always needs to be larger than 0. So that's the only additional complexity we put in this covariance component estimation business. So it's not really that getting that more complicated. And we could now actually estimate these parameters lambda I. So of course we still need to estimate parameters. And before we needed to estimate beta and sigma square. And now we need to estimate beta and lambda 1 to k, where in fMRI this then corresponds to, for fMRI, this corresponds to beta lambda 1, which is still the variance of the errors, because it relates to the identity matrix, and lambda 2. Now, so we just have one parameter more. That's the whole thing. We could do this using maximum likelihood. And in the third book, you can read all about how this works for maximum likelihood. However, as I said many times now, in neuroimaging, this is done using Ramel. So read the third book, it's really a nice book. But we are looking at it when we are looking at neuroimaging. So we are now doing model estimation using Ramel. So model estimation under Ramel. The basic idea of Ramel is to estimate the error covariance parameters after removing or in a GLM where the X beta, so the deterministic effect, or in the literature you always also see this as being referred to as the fixed effect, but this is our deterministic expectation having been removed. And this is in some way similar also to what we did last week in Generalized least squares. So do you also watch that video? Do you remember what the basic idea of Generalized least squares was? To get to the generalized least squares estimator?
We are trying to find the best fit. We are trying to find the best fit.
No, that's ordinary least squares, and but I'm referring to generalized least squares that we discussed in the second hour last week.
We need to study.
We need to watch it again.
So the basic idea of generalized least squares was to make the error terms that were correlated to make them uncorrelated. So we used a matrix multiplication to basically get, sorry, I think it was like, to get to to get to a spherical GLM. Yeah, so the idea was we multiply the entire GLM equation by a matrix such that the errors become uncorrelated, and then we use the standard beta estimator in this transformed GLM, and then we back transform to the correlated case. So basically the whole thing was based on multiplying the GLM, doing the estimation in the transformed GLM, because there the standard beta estimator applies, and then looking how the standard beta estimator looks in the untransformed case. And the logic here for Ramel is somewhat the same. So again, we use a matrix multiplication to get to a form of a GLM that is different. We estimate the parameters in this different form, and then we return to the form that we actually use. So it's again this transformation of a GLM, estimating there, and then back transforming the estimates. The fundamental idea here is, I need to watch time a little bit. The fundamental idea here is to multiply the GLM with a matrix K, with a matrix K, and which is n times r dimensional, such that kt times x is the 0 R times P matrix. Yeah. So we assume that this is somewhat like last week. We assume that we can find a matrix K that, when we multiply it with the design matrix, yields the 0 matrix. How we find this matrix K, we don't discuss now, because it will turn out in the very end, when we discuss the Fischer Scoring algorithm, that we actually don't need to specify this matrix K. So the estimators that we will come up with for the lambda parameters, they will not depend on the matrix K. So this K matrix in Ramel is just an imaginary matrix, if you want, that motivates the whole thing, but it turns out that the precise form of K does not enter the estimates, so we don't actually need to specify it. It's a little bit different to generalized least squares, where we got this matrix that we need to multiply everything with from the square root of the covariance matrix. So there we have this thing that we need a matrix K like this, but this is in the GLS setting, and there we actually need this matrix K in the end when we want to compute estimates. Here we this matrix K, which is a different matrix, of course, because it's satisfying a different constraint, we never really need, but we need it to develop the theory, which is a little bit something to get used to, but that's nevertheless how it is. So the fundamental idea is that there is this matrix K, which we multiply with the design matrix to get a 0 matrix. This matrix K is also called error contrast matrix. Don't think much about this term, because it will just don't think too much about this term. It's just how it's often referred to. The point is that if it's multiplied with the design matrix, it yields the 0 matrix. Now, let's have a look. So our GLM looks like this. And now we multiply the whole GLM with KT, like we did that last week, and we have a look at what happens. So if we now apply this transformation, of course we cannot really say something about KTY, but we can say something about this thing here, because KTX is 0, so KTX will be KTX beta will be 0 R times P times beta, which is P times 1. So oh, there's actually a typo in the script. This will be the 0 vector here. And our epsilon is still 0 n d lambda. Yeah. So the important point here is that we get rid, because we define the matrix K such that if it's multiplied with the design matrix, we get the 0 matrix in this transformed GLM. So this is here the transformed GLM. There are no beta parameters. Yeah, so we removed This is what they always call remove the fixed effects. We remove the deterministic aspect of the GLM. Yeah, so we now deal with the GLM in which there are no beta parameters. There's just the errors. Yeah, and if we actually apply this here, so the transformation of the errors, then we can of course rewrite our GLM in terms of a PDF over KTY, because this will be KTY 0 R KT epsilon K. So this is again our linear transformation theory for Gaussians, which we also used last week, and we used when we talked about the beta parameter estimator distributions, and which you also have studied for the exam on the 20th, because it's part of the Gaussian preliminaries. So that's that. Oops, sorry, not the epsilon there, sorry, the V lambda. So this is, yeah, essentially this is just transforming the errors, which were distributed according to this multivariate Gaussian, and because they are multiplied by a matrix KT, they end up for the distribution of KTY in the covariance setting. And I think this is where I want to stop today, because the problem of restricted maximum likelihood estimation is then actually to do maximum likelihood estimation of lambda maximum likelihood estimation in this transformed model. Yeah, so we don't have to estimate any beta parameters in this transformed model because there are none, but we can estimate the lambda parameters. And then the idea will be, once we have estimated the lambda parameters, then we have an estimate of our V matrix, which we can use in the generalized squares estimator to also estimate our oops, that's a little bit too much, to estimate the beta parameters. Yeah? So if you're wondering what happens with the estimation of the beta parameters, we will get to it. Was a little bit weird here. What's going on? XT. Let's forget about this. I'm not quite clear on this right now. We will do maximum likelihood estimation of the lambda parameters in a numerical setting in this thing. This is restricted maximum likelihood estimation. And once we have our lambda hat, we can use the generalized least squares estimator to also estimate the beta parameters in the original GLM. And then we have everything. And so next week we will start with this likelihood function for lambda, and look how this can be estimated. And this actually needs numerical estimation, so we will use Fischer Scoring algorithm, which is a variant of Newton-Raphson, of a multivariate Raphson thing. And this is what we will discuss next week. Yeah. So again, the fundamental idea of Ramel estimation is to transform the GLM that we are interested in. The GLM that we are interested in is now the GLM with these covariance components, so with this thing. And then we estimate in this transformed GLM. Once we have estimated there, we use our results to go back to the untransformed one. Yeah? Good. Questions for now? Good. Then let's stop here and continue next week. And then let's go. So the topic today is the Ramel Fischer Scoring algorithm. And if you go to the Google folder, the lecture script is now updated with respect to Ramel and also the nonlinear optimization stuff. So you can see that in there. Wasn't there last week? So the Ramel Fischer Scoring algorithm is the algorithm that is always run when anyone analyzes fMRI data in the framework of the GLM in the world. So it's run a lot of times, although I think most people don't. Well, they should know that it's being run because it's printed to the, as we saw last week, it's printed to the MATLAB command window. So it's saying Ramel iteration 1, 2, and 3, and so on, but it's not much talked about, strangely. Anyway, so yeah, today we want to then look into how Ramel estimation is actually numerically carried out. But the first thing we want to do is give a little bit of a recap of what we've done so far with Ramel. Once we are again in the position where we have the Ramel objective function and understand what that is, then we're going to look into the nonlinear optimization of, or the, let's say, the numerical optimization of this using what is known Fischer scoring. And Fischer scoring is a variant of Newton-Raphson optimization. So we're first going to look at Newton-Raphson optimization. Once we establish this, and specifically the multivariate form, then we can easily discuss Fischer scoring. And because this is a general algorithm, we then finally have to look at how Fischer scoring is applied to the Ramel maximization. So that's the plan, and once we're done with that, we're actually done with the Ramel business, and after Christmas then get started on stochastic processes and how they relate to the covariance matrices that we are discussing here, and then also the spatial expression of effects, so the random field theory based p-value evaluation. But that's for the new year, so let's start with some Ramel recap. So last week in this one video, which unfortunately was not recorded or somehow didn't work, we looked at the motivation for doing Ramel, where the basic motivation was that the standard maximum likelihood estimator for the variance parameter is biased, so its expectation is not equal to the true but unknown variance parameter. And then we looked a little bit how this into how this bias arises, because in the maximum likelihood estimation of the variance parameter, one plugs in the beta parameters beta parameter estimates, and this plugging in of the beta parameter estimates then ignores some contribution to the log likelihood estimator, as we've seen. And so that was kind of the motivation to start with the Ramel business. And another thing that we introduced last time was then to consider now the GLM as it's actually formulated for fMRI data analysis, namely with non-spherical and linearly constrained covariance matrices. So what I mean by this is the following. So in terms of the model that we look at, we now look at a model that has parameters beta and lambda for a data vector y, and this is given by y by a multivariate normal distribution over the data vector y, which is of course still our time series of MR signals over a single voxel, which is distributed according to a multivariate normal distribution, and this multivariate normal distribution has an expectation parameter x beta, which is still of course our design matrix, which we get from the convolution of the onset functions. Beta parameters are still our effect sizes of the conditions, but the important thing is now that we don't have as the covariance matrix parameter, we don't have this spherical covariance matrix sigma square In, which models independent and identically distributed errors. So that's not the case, but we have this V lambda, and this V lambda we introduced as the sum of covariance component parameters, these small lambda I, and covariance matrix basis functions Qi, where we also have seen that Q1 is always the identity matrix In. So we, with lambda 1 being larger than 0, we cover the spherical error covariance matrix, but we can do more. And for example, we've seen that in fMRI, what is often used is this ZT matrix, where where the entries of Z are given by this exponential, do it correctly, this exponential of the distance between J and I, so the row and the column matrix coordinates. And why this exponential, so why this Zij matrix is being used, this is what we're going to look at in the new year in January. I want to know a little bit about stochastic processes. So at this point it's not really meaningful. It's modeling some decaying correlation between the errors. That's what you may appreciate, but really where it's coming from we don't know yet, but it's fine because we will look into that, and we need some more theory in any stochastic processes to really understand this. The important thing is that this V lambda is now not only the spherical covariance matrix anymore, but possibly more. And then the story in fMRI GLM analysis is that Ramel is now used to estimate the lambda parameters. So in a way we have Ramel estimate lambda, and then we have a lambda estimate from Ramel. How exactly we get to that we will see today. And then we can of course estimate beta. So in a second step then estimate beta using the generalized least squares estimator. So basically doing, so I get that correct, so basically by using an estimated covariance matrix in the beta estimator. Another way we can do is, of course, to whiten the data, as we discussed in generalized least squares. But that's the overall procedure, and we discussed generalized least squares, and we did a little bit on Ramel, and today we will more, and so we will finish this first step here today. So that's then the overall logic and the overall model, and then we started talking about the idea of Ramel estimation, and the main idea of Ramel estimation is to multiply the GLM equation, which takes, in our case, or in this case now, the form this form, to multiply this with a matrix K transpose, where K is n times, sorry, not n times P, Jesus, is n times R, sorry. And the important thing about this matrix, which is also called error contrast matrix, which is just a name, is that if it's multiplied with the design matrix, it yields the R times P zero matrix. We will never really talk about how this K matrix is found, because what we will see in the end is that we don't actually need this K matrix at all to estimate lambda. So it's kind of a theoretical construct that is put in, but which we never really have to evaluate to actually do Ramel estimation. When we then multiply the GLM here, so if we take this times KT, what we get is KTY equals KTX beta plus KT epsilon. And the important thing is that this is zero, so this entire product of x and beta is removed, and we get KTY being just KT epsilon. So we in this transformed GLM we don't have any contribution of these fixed effects, but we just have some transformed residuals. And with essentially the linear transformation theorem for Gaussian distributions, we then immediately know that KTY is distributed according to a multivariate normal distribution. Still a typo. I had hoped I'd get them out, but there's still one. With zero expectation and with covariance matrix given by the transformed error covariance, namely KT V lambda K. Yeah, so this is all now, after multiplying the GLM that we are working with this matrix KT, we get to a distribution of the data multiplied by KT that is distributed according to a multivariate normal with r-dimensional zero vector and covariance matrix KT V lambda K. And the task is then to estimate the parameters of this distribution based on KT y and essentially y, because k is somehow given, we will not need it, but y is the data. The only thing that there is to estimate is this lambda covariance component parameter vector, because there are no beta parameters anymore. Yeah. So because they have been removed. And this is then done using essentially maximum likelihood, but because we have already restricted this maximum likelihood to the case where the beta parameters are removed, this is referred to as restricted maximum likelihood. And the log likelihood function that we are dealing with here I then denote as LKTY, which is a function of a k-dimensional parameter lambda, gives a, like always, a real number, and takes this form, which just follows, as you also see in the script, which just follows from taking again the log of this multivariate Gaussian, and then you get to this form. A bit too big. Maybe I go into a second row here so that we see the whole thing. Yeah, so this is just the log of this multivariate Gaussian, and then viewed as a function of the lambda covariance component parameters. So it's essentially completely the same as in standard and maximum likelihood, but because we have this kty constraint here, it's restricted. It's called restricted maximum likelihood. And so you might miss, like for the Gaussian, some minus something here, and no, here and here. But this is of course because the expectation is 0, so minus 0 r is just 0, and this is the inverse covariance matrix, so it's actually quite straightforward. And one thing that can be done, and that where somehow the magic of Ramel is actually happening, is that one can define a matrix P lambda, which has this form. One can actually view this matrix from a Bayesian perspective, but we will not do this. So if we define this P matrix, you see that this P matrix, that there is no K in this matrix, so it's just derived from the inverse of the covariance matrix, so V lambda, and the design matrix. The peculiar thing, as I write in the script, is that this matrix P lambda is equal to K, KT, B lambda, K minus 1 KT. And that's actually quite important. So that's so if you look at this, this matrix, so with all the V's and the inverse V's and the design matrix, it's equal to this product of the covariance matrix with this K matrix. It's not easy to see, or at least I don't see immediately why this should be the case. I looked into the mathematical derivation of this, and it turned out that this is actually quite involved. So because there are always time constraints, I decided I will leave this for the moment and not study in detail why this is happening, because it really seems to require some abstract matrix algebra theory, and I just didn't have enough time to really go deeply into it. You find a proof of this identity, so that this V lambda minus 1 x and so on is equal to this K. You find a proof for this in this very nice book by Searle on variance components in an appendix. So if you really want to know why this is true, which is of course interesting, you find this in the appendix M4R of Searle's variance components. But yeah, maybe notice that when I looked into it, I found it to require some work for me to understand what's going on. So I don't know what that means for you, but yeah, it's definitely, it's very important result in the whole context, because it will then allow us to rewrite the Ramel objective function, or this Ramel log likelihood function, in a simple way. And actually, because of this identity, so that something with the k, namely p lambda, is the same as something that only involves the covariance matrix V lambda and the design matrix, we get rid of k to a certain degree. And so it's important, but it's really mathematically deep. So yeah, so this is why, although I usually don't do that, but this I take here as kind of a result that we don't prove and we just take for granted. With this result, however, and specifically with this thing here, we can substitute a little bit in the Ramel log likelihood function. So we can basically replace this k, kt, v lambda, k minus 1, kt here. So this can be replaced by p lambda, and then we get kind of a simplified version of the Ramel log likelihood function, which is also known as the Ramel objective function. So you often see the term Ramel objective function in the literature. So that then looks like this. And we can replace all this stuff here with this P matrix, so we get P lambda Y. Yeah? And this here, what I've just wrote down, this is then known as the Ramel objective function. So of course just the log likelihood function in the Ramel scenario with this P lambda put in, was referred to as the Ramel objective function. So this function now is a function of lambda, so our covariance component parameters, but these lambdas, they come in, of course, here at v lambda, where they are the weights in this linear combination of basis functions, and they come in here in the p lambda function in the inverse of the covariance matrix. So the important thing here is that this function is nonlinear in lambda, because it enters through a determinant and it enters by its inverse, both of which are nonlinear functions, and hence it's not readily possible to solve this as we did, for example, for the beta parameter or the variance parameter in the spherical case. So it's more complex to solve. So to not really to solve, but to maximize with respect to lambda, and hence what is used here is a numerical optimization method. So instead of having now a optimization, so instead of having a formula like our beta head estimator, which was just a simple formula that we can always apply once we have the design matrix in the data, we now don't get a simple formula for lambda, but we need to basically shift lambda around, so to maximize the function or the Ramel objective function as a function of lambda. Yeah, so that's kind of the this is when you see these Ramel iterations in SPM happening. And this is when lambda is shifted around until the Ramel objective function is maximized, and once it's maximized, then we of course have our lambda Ramel estimate, and which maximizes the Ramel objective function. And the question then is, how this numerical optimization is happening. And this numerical optimization of the Ramel objective function, in terms of how it's implemented in SPM, this goes back to 2 papers by Carl Friston in 2002 and 2003, which discuss that to a certain degree. So this is kind of the best documentation you will find on what SPM is actually doing. I'm not saying it's an awesome documentation, but at least it mentions that it does Ramel, and it provides the Fischer Scoring update equations without really discussing Ramel, because it's doing it in a different context. But that's how it unfortunately is. It would be better if this would be much better explained and much better documented. But what can you do? So that's kind of now the aim, to maximize the Ramel objective function. Yeah? And once we have the maximized the Ramel objective function again, then we have our lambda hat Ramel, which is then of course also an unbiased estimator of the variance components, which we can then put into the better generalized least squares estimator, or we, and this is actually what's happening under the hood of SPM, we can use the estimated covariance matrix to whiten the data, so by multiplying with its square root. But this is equivalent as we've seen previously. Good. So the aim then is to discuss how now this Ramel objective function is maximized. Yeah, and how this is essentially done in SPM. And this now takes us kind of out of just discussing statistics, but takes us into questions of numerical optimization. So this is why there is now this additional mathematical preliminary section, which is actually just a couple of pages. It's just 4 pages on numerical optimization. Of course, this doesn't cover numerical optimization as a whole. I will, once I get back to finishing the PMFN book, I want to put in a couple of other things into this numerical optimization thing. Right now it focuses on Newton-Raphson, because Newton-Raphson is the precursor to Fischer scoring, and after all, because here we need to discuss Ramel Fischer scoring. To maximize with respect to lambda. So that's then the main topic actually for today. And maybe let's just start with some background on numerical optimization. So the fundamental The fundamental aim of numerical optimization is, of course, to find some maximizing argument. So if you have a function of some theta, so some parameters, you want to find a theta star such that this function f at the location theta star is larger or equal to itself for all theta not equal to theta star. So that's the main aim. Of course, you can easily visualize that and then think of some function that maybe in this form will never really exist. Well, it could be a Gaussian mixture or something. And you want to find the maximum of this function. So this is here f theta. Here you have the parameter space. And of course you see that the maximum of this function here is here. So that's the maximum. And here f theta star is larger or equal to f theta for all the remaining parameters. And then of course the maximum happens at this location. Yeah, so it's intuitively numerical optimization is of course fairly straightforward. At least the aim of numerical optimization is fairly straightforward. You want to find what I call a maximizer or a maximizing value. And of course, this maximizing value of the input parameter of this arbitrary function here, f, corresponds to the location of the maximum. Yeah? So just keep that, because people often confuse that. They say we want to find a maximum, but then they actually mean they want to find the input argument that maximizes the function, and this is not called the maximum, but this is called the maximizing value or maximizer or whatever, but not maximum, because the maximum is the value of the function at the location of the maximum. So that's the aim of numerical optimization. And of course, in our case now, this function that we are here interested in is our Ramel objective function. Yeah, so I'm just writing f here to make it a little bit more general, but of course what we have in mind is to maximize our Ramel objective function. And then the basic idea of numerical optimization is that you start with some value, theta 0, so you come up with some starting value in whatever way, yeah, maybe let's make this in blue. So you start with some starting value, and then you somehow try to have a rule that gives you that based on a starting value gets you to a new value of theta. So for example here theta 1, such that the new value is somehow larger than the old value. So you here get from f theta 0 to f theta 1. And so you proceed over iterations, so you go theta 0, theta 1, theta 2, and so on, until convergence, whatever that means in a specific scenario, with the aim of approaching the maximizing value in parameter space, or finding the maximum. And there are just very many approaches to do that. So one way to do that, which I also have included here, mainly because you hear all about it in terms of deep learning, is gradient ascent. So one, just to briefly mention it, gradient ascent is a specific rule to shift around the parameter based on the gradient of a function. So I assume, because some of who is taking the exam tonight? So whoever's taking the exam tonight knows what a gradient is. The other ones will know it in February. It's essentially the first derivative of a multivariate real-valued function. Gradient ascent is a specific rule to do this kind of parameter search and finding the maximum. And the update rule for gradient ascent is that for the k+1 iteration, so the k has nothing to do with our covariance components, now it's just the iteration counter here. You take the previous parameter and you add to it a learning rate times the gradient of the function at the previous location. So that's the gradient, so the first derivative in theta k. And because the gradient is always points in the direction of steepest ascent. So for example, if you here have kind of this gradient, so you would go a specific amount in this direction on the function, which in parameter space takes you a little bit into this direction. The problem with gradient ascent is that you need what's called a learning rate parameter, so this alpha, and this alpha basically says how far you want to go along this gradient. And of course, if you say very little, then you make very little progress. If you say very far, so for example, you go up to here, then you actually don't even increase necessarily the value. So gradient ascent is in general quite a bad idea if it doesn't have an adaptive learning rate. So gradient ascent in terms of nonlinear optimization is really not the most useful algorithm. It works roughly, and if you basically test a lot of parameters, then and always check whether they are at a maximum, or if you're trying to minimize something at a minimum, they still do something, but it's not the most clever algorithm. And a little bit more clever than gradient ascent is actually Newton-Raphson, which we now want to discuss. So that was briefly the general idea of numerical optimization, which of course in terms of people working in science, I think people like numerical optimization more than analytical optimization because you don't have to think that much. So in terms of numerical optimization, we have kind of an algorithm that finds you the maximizing value of a function, and if you want to do analytical maximization, you have to actually do what you always need to do. You evaluate the necessary and sufficient conditions for a maximum. This was actually an important point that I forgot to mention. What you always try to do in terms of maximization is that you want to find a point that satisfies the necessary condition for an extremal value. So you always want to go to a location such that the gradient, so the first derivative of the function, is 0. So this is what you want to find, because if you look here at the maximum, the derivative is just the slope of this tangent line, and that's 0 here for this kind of global maximum. But of course, it's only the necessary condition. So you also have, for maximum, you also actually have this as local minima, and you also have this at local maxima. So it's not really any proof that you found the global maximum. You also have this at saddle points, but it's an easy to check indicator, and if things increased while going there, and then you are there, and the first derivative is 0, then this is usually a good indication that you're at a maximum. I forgot to say that you can of course do more sophisticated things and also look at the second derivative, but specifically if you have multivariate real value functions, this can be a little bit complex. So the basic check is always that the first derivative is 0. Now, Newton-Raphson. Newton-Raphson is kind of a little bit more advanced approach compared to gradient ascent, and the aim is here to maximize a function f. So I'm starting with the univariate Newton-Raphson approach. So you have a function that is a real valued univariate function, and the aim is to find a 0 of its derivative, because if you are maybe let me first write it down by finding 0 of f prime. So the motivation here is that if the first derivative is 0, then you are at an extremal point or saddle point. But usually if you have functions that are well behaved, for example functions that have a square and are the negative of a square, then from finding a 0 of the derivative of the first derivative, then you are likely at a maximum. Yeah. So if one really wants to do this mathematically more rigorous, then one would have to study the properties of the functions and make sure that for the functions that you apply this to, it actually holds that if the first derivative is 0, that you are at the location of a maximum. So, and for most of the functions that we are dealing with in statistics, you actually can do this, but of course this requires more theory, so we will not discuss this in detail. So we are happy with the intuitive idea that, okay, at a maximum, the necessary condition is that the first derivative is 0. So if we find a 0, so basically by a 0 I mean of course a point f theta star, f prime theta star, where this is 0. If you find a 0, then you are at the location of a maximum. So that's kind of the idea. And to do this, the idea is to use a first order Taylor approximation. Again, people who take the exam today know what that is, and also should know. So there's still time. To look at the first order Taylor expansion of the derivative, which I actually denote here with this little tilde thing, so that it's clear that it's not the derivative itself, but an approximation to it. And this first order approximation is done in the expansion point theta k. So we assume that we know some value for the parameter, which can of course be then our starting value of the algorithm, and we approximate the derivative of the function f prime. We approximate the derivative of the function f, which I denote by f prime, by a first order Taylor approximation, which then of course actually, there's 1/2 missing. There's my 1/2. Or did I somehow get... no, sorry. There's no 1/2 missing. Sorry, I always get confused there. This is a first order Taylor approximation of f prime. And of course, a first order Taylor approximation usually involves the function itself plus the derivative of it times the difference between the expansion point and the value itself. And here, because the function for which we do the first order Taylor approximation is already the derivative, this is why we here have the second derivative, which makes it look a little bit like a second order Taylor approximation, but it is not one. So we approximate, or the idea of Newton-Raphson is to approximate the derivative of f, for which we want to find a 0, by a first order Taylor approximation, and then to solve this analytically. So that's the idea. So the trick is then that you want to find a point for which this thing here, so I'm calling this theta tilde, could also call it theta star, maybe I call it theta star because I just called it theta star, equals 0. Yeah, so this is kind of the approximated 0 of first derivative. Yeah, somehow we want to find a 0 of the first derivative, it's not really clear how we should do that. Newton-Raphson proposes, okay, we find a zero of a first order Taylor approximation to the first derivative, because we can actually do this analytically. And maybe let's do that before the break. So we now want to actually solve this equation here for theta star. And this one can readily do by basically filling in what f tilde prime is. Namely, it's f tilde theta k. That's the expansion point. And this is set to 0. And now we have to solve this for theta star. And of course we can first put the f prime theta k to the other side. So we get f theta k theta star minus theta k equals minus f prime theta k, and then we can divide by the second derivative. The expansion point, and then we can take this to the other side. And this is then the zero of this approximate first derivative. Well, so we can find a zero of this approximate first derivative based on some value theta k by taking theta k and subtracting from it the value of the function f prime at the location theta k divided by the second derivative. And this then is the basic idea for this algorithm. So we do that once, but we have approximated it, and maybe we are not really at a zero yet, so we do it again and again and again, and we get to the Newton-Raphson update. Which is just what we've just written, but for the next, so for k plus 1, we use what we derived here, theta k minus f prime theta k divided by f2 theta k. And we do this until f prime theta k plus 1 equals 0, because then we have found a 0 of the derivative, which then hopefully corresponds to a maximum of our original function. Yeah, so this is the Newton-Raphson update rule, again, which derives from approximating the derivative. And I think this is a good time for a break, and after the break I show you a picture that shows what's happening there, and then we can generalize this easily to multivariate Newton-Raphson, and then can easily generalize this to Fischer scoring, and then we are done. Yeah. Okay, so let's have a break if there are no current questions. No? Good. Good, then let's continue. So first, a visualization of what we've just seen. which is here. Let's see. So what we are interested in, So what we're interested in is this derivative of the function that we want to find a maximum of. Yeah, so this is this f prime theta. So theta is the x-axis here, and we assume that this derivative has a zero, so a point where it's zero, which is here, because we assume that the function f itself has a maximum, and at the location of the maximum the derivative is zero. And then what's happening with the update rule that we've just described is that we first start with some theta k. This can be, of course, be theta 0, so our starting value for in this numerical optimization. And then what we look at is the first order Taylor approximation to the function f prime in this location, and this is this red line here. There's actually a little bit of a typo. Oh no, it's not really a typo. So what I'm saying here is that this approximation, so this f tilde prime theta changes. Of course, it also changes with the iterations because it's always in a different point. So I'm giving to the approximation, I also give an iteration index. Yeah, so but this is, so the red line here is the first order Taylor approximation, and then what we did when we shuffled things around and solved this, we identified the zero of this first order Taylor approximation, which is here. So this is our theta k plus 1, and because what we actually want to find is this point, but of course if we use a first order Taylor approximation, we only look at a linear approximation of that, which is locally good, but globally maybe not so good. And as you can see, we are still quite far away from the actual zero. And then we do the same thing again in this new theta k plus 1. We again look at the first order Taylor approximation, which is this straight line here. Again, solve for the zero of it, and then at theta k plus 2. And then we would do the same thing again, and well, maybe I should have plotted it, but I didn't. We would, at this step, roughly then be actually at the true minimum. Yeah, so that's kind of the visual intuition of what we've done. So the important thing to always remember what this is trying to do is to find a zero of the derivative of the function that we want to maximize, and then this update rule can actually makes some sense. Questions about this? No. Good. So what we've just seen now on the slide is actually always solving for the zero of this first order Taylor approximation to the derivative, which is given by this. And this now was for the case of trying to for maximizing a univariate real-valued function. So a function that maps the real numbers onto the real numbers. Now we've already seen that when we want to maximize the log likelihood or the Ramel objective function, this is not a function of the real numbers to the real numbers, but it's a function of k real numbers to the real numbers. Yeah? So it's a multivariate real-valued function, so it takes in our lambda, which is a k-dimensional vector. Yeah? Again, k here is the dimension of the lambda, this k is the iteration counter. Two different little k's. So that's then the next step we want to take. So to basically generalize the Newton-Raphson rule for multivariate real-valued functions. Which I think I also call the multivariate Newton-Raphson method. So let's have a new headline here. The multivariate Newton-Raphson method. It's just the Newton-Raphson method applied not to a univariate real-valued function, but to a multivariate real-valued function. And that's fairly straightforward. The difference now is that our function here, I use for the number of parameters now a p, otherwise, or doesn't really matter. Let's use k because for we will use it for the Ramel function. So we have a function that takes a k-dimensional input vector and maps it to a real-valued function. And so we have this theta parameter, which is of course will be our lambda parameter mapped to f theta. And the only thing that changes in terms of the logic of the update rule is that, and I'll now take I for the counter so that it's not our k. So theta is k-dimensional now. What changes in terms of the update rule is that we replace the first derivative of the function f by its gradient, because the gradient is the multivariate analog of the first derivative, and we replace the second derivative by the Hessian of the multivariate function f, because the Hessian matrix is the multivariate analog of the second derivative. So otherwise this algorithm and this update rule look exactly the same. So we subtract the gradient of f at theta k, which is of course the vector of the partial derivatives of f, as you know from the mathematical preliminaries. And this division by the second derivative is of course the same as the inverse, so the multiplicative inverse of the second derivative. And because you cannot divide by a matrix, as you know, but you have this kind of matrix division form, which is called inverse, we take the inverse of the Hessian and pre-multiply the gradient with it. So that's the idea. So the logic here, so if you compare this, so this is of course f prime theta k, and this here is 1 over f2 prime theta k. Yeah, so this is a completely analogy, just that the first derivative gets replaced by the gradient and the second derivative gets replaced by the Hessian, because these are the multivariate analogues of the first and the second derivatives. You can also see from this, if you want, that you here have kind of, you can also see this as a gradient scheme with an interesting learning rate. So you can roughly understand this as a gradient ascent with an update or a step size parameter alpha that is specific to each of the gradient components. So it's not just one scalar parameter multiplying the entire gradient. And this alpha parameter is given by the inverse of the Hessian. So if you want, you can understand this as a kind of specialized gradient ascent if you want, but you don't have to. So that's the multivariate Newton-Raphson method. Looks a little bit shitty, but anyway, sorry. So this is inverse Hessian. And this is the gradient. And this is already the multivariate Newton-Raphson method. Now, the next thing from the multivariate Newton-Raphson method is already a Fischer scoring, which is a multivariate Newton-Raphson method. So that's multivariate Raphson for a log likelihood function. So if your function f that you're trying to maximize is a log likelihood function, then Newton-Raphson is called Fischer scoring. Fischer scoring is described in the script in the part on probabilistic inference. So it follows. So there's some discussion of the analytical way to maximum likelihood, and then there's 10.3. There is a brief section on Fischer scoring, which essentially says that Fischer scoring is multivariate Raphson applied to a log likelihood function. And Fischer scoring in the logic, it's exactly the same, but what is different, or what is special, let's say, is that it's applied to a log likelihood function. So we assume we have some log likelihood function. Well, maybe let's use k here again for the number of parameters, and it's mapped to the real numbers, and our theta is mapped to Ly theta, which is a log likelihood function. So it's somehow the log of some py, which of course for Ramel is the log of, as we've seen, the log of p lambda k t y. Yeah, so this is what we want to get to in the end, but for the moment we are dealing with a general log likelihood function, not necessarily the Ramel objective function. And then what happens is that Fischer scoring, that the components of the multivariate Newton-Raphson method, namely the gradient and the Hessian matrix, get special names in Fischer scoring, but they remain what they were. Yeah? So the gradient of a log likelihood function is referred to as score vector, but that's just the gradient of the log likelihood function. And yeah, we denote it here by s theta, which is just the gradient of a log likelihood function. Didn't really introduce this y, so we can also get rid of it. And the negative Hessian, so the Hessian matrix with a minus sign in front of it, is referred to as Fischer information matrix. And that's usually done because information has an I. So that's the negative. So we need a minus sign. The negative of the Hessian matrix of the log likelihood function. And then one final thing that is often used in Fischer scoring is instead of using the Fischer information matrix, the expected Fischer information matrix is used, because you may remember that a log likelihood function, of course, depends on the data. The data, of course, is random, so the log likelihood function is random. Also, the gradient then of the log likelihood function is random, and also the Hessian matrix, which is just derivatives of the log likelihood function, they are all random. And when one can compute the expected value with respect to the data distribution. And this is then known as the expected Fischer information matrix. So that's the expectation under the distribution of the data of the Fischer information matrix. That's why we don't have here. So of course, how this looks in detail, this then depends on the log likelihood function. Yeah? If you have a log likelihood function and you want to do Fischer scoring, you need to compute its derivative and you need to compute its Hessian matrix. And then once you have the Hessian matrix, you need to evaluate its expectation with respect to the data. We will see that at least the solutions for the Ramel Chapter function in a second. But with this kind of nomenclature, Fischer scoring then corresponds to multivariate Raphson. To the multivariate Raphson method. So what we replace here is the inverse Hessian with the negative Fischer information matrix. So this minus becomes a plus, and we replace the gradient by the score vector, and then we already have Fischer scoring. So Fischer scoring then takes the form, do we have k or I? I plus 1 theta I plus the expected Fischer information matrix, and of course the inverse of that as well. It's the inverse of the Hessian, and S theta, oh now I'm forgetting the iteration counters. Yeah, but again, not much has happened since we introduced univariate Newton-Raphson. So again, think of if you think about the univariate Raphson, this is still 1 over the second derivative, and this is still the first derivative. Yeah, so conceptually, this is still our. Let's go back. Our Newton-Raphson update. It's just that the first derivative of the function that we're interested in is now called score vector, and the second derivative is called expected Fischer information matrix. But these are just new names for conceptually the same things. Yeah, so that's this kind of algorithm. So the multivariate Newton-Raphson method applied to a log likelihood function where the gradient is called score function, and the Hessian matrix, the negative Hessian matrix, is called Fischer information matrix, and usually its expected value is used, is called Fischer scoring. That's just how it is. But it's conceptually it's univariate. It's the picture that I showed you before. It's univariate Newton-Raphson in a multivariate setting. Good. So with this, we now actually have everything that we need to maximize our Ramel function. So let's go back to Ramel now and do Fischer scoring for Ramel. And basically, let me tell you what SPM is doing when people all over the world are clicking estimate. Fischer scoring for Ramel Maximization or Ramel Estimation. So again, the function that we want to optimize is a log likelihood function. It's the log likelihood function of this transformed data. We have k lambda parameters. So like I told you, in fMRI usually k will be 2. So we need the multivariate Raphson method, and because we apply it to a logarithmic function, we call this Fischer scoring. And then our function looks as follows. So this is again the function that we've seen this morning, like ages ago. Minus 1/2 y t p lambda, where we defined, or where our p lambda is our K matrix kt v lambda k minus 1 kt, which is also v lambda minus 1 minus v lambda minus 1. Gets a little bit longish, but that's just how it is. Yeah, so this is where we want to apply Fischer scoring now, which means we need the gradient of the Ramel function, and we need the expected Fischer information. But based on what we've seen here, we can already write down the algorithm. So yeah, the algorithm then is, we start with some values for lambda, some initialized values for lambda, and then we update lambda according to the Fischer scoring rule. So we take lambda I plus the expected Hessian or Fischer information matrix. Here I actually write the Hessian. Look, doesn't really hurt, it's more explicit to use the Hessian at lambda I. And can we take the inverse of this and multiply this with the gradient of the Ramel objective function. Yeah, so that's the Fischer scoring update rule for the lambda parameters. Now that's all very nice, but the problem is if we really want to implement this on a computer, then of course then we need to know the gradient and the Hessian matrix. And these now, and also the expected value of the Hessian matrix, and these can be computed analytically. At least yesterday I was able to derive most of it, except for this last expectation. So if you look into the script as it is right now, you see that there are now formulas for the gradient of the Ramel objective function, and also for the expected value of the Hessian, and there are proofs. So I will not discuss the proofs now, so how this is calculated. So you can look at it, it needs some matrix calculus, so it's a little bit more advanced calculus because you need to compute derivatives with respect to scalars that factor into matrices. So it's a little bit advanced matrix calculus, but it's doable if one buys into the rules of matrix calculus. So the proofs, except for the proof that one part, one little proof in the very end where the expected value actually gets rid of some term, that's not in there because I couldn't figure it out. maybe I will be able to do it that soon. So these equations and their proofs are in the script, and I will now just give you the equations, and yeah, you can then basically decide for yourself how deep you want to go into the proofs. So the gradient of the Ramel objective function evaluates to -1/2 the trace, which is the sum of the diagonal elements of p lambda qi plus 1/2 yt p lambda qi p lambda y, and this is the ith component of the gradient. So remember, the gradient are all the partial derivatives. So the partial derivative with respect to lambda 1 is this expression with q1. The partial derivative with respect to lambda 2 is this with q2, and so on. And for p lambda, you of course always need to put in this, and this is the gradient at lambda. So if lambda is lambda I, of course, then you need to put in lambda I here. So that's the gradient. That's actually fairly straightforward to derive, as you see in the script. The Hessian evaluates to, this is of course a matrix, so you have ij components. This evaluates to 1/2 the trace, so the sum of the diagonals of p lambda qi p lambda qj, which doesn't really matter because it's in the trace, but nevertheless qi plus 1/2 yt p lambda qj p lambda qi y. So these are the elements in the Hessian matrix where I and j both run from 1 to k. And now the expected value in there, this is the only thing that I'm not quite certain yet why this is the case, and haven't really found a good proof. So the expected value of the Hessian matrix apparently is only the first term here. Well, it's plus the first term. So there seems to be something going on in terms of, so the expectation of this, of course, is just this, and the expectation of this is not quite easy because it has a y in a square in it. So you have the square of y. So this would then go somehow in the direction of a chi-square distribution, and one would need to look into its expected value, and maybe this is then just this, and then you have this plus this. I'm just not quite sure about how this last expectation comes about, because yesterday my energy then was over once I get to the Hessian, and yeah, so I would have to think a little bit more. But that's then the expected value of this Hessian. So then if one puts this into the Fischer scoring algorithm that we wrote kind of analytically there, if we now substitute the gradients and the expected Hessian, then we get what you actually see also in these papers from the early 2000s, namely you here have the inverse of the I don't want to. I think this is still a little bit I shouldn't write. Oh, let's try it. Okay, so because you need to be a little bit careful here, because the gradient now has the form -1/2. Oh, let's write the whole thing up, then it's maybe easier. So the gradient is q1 plus 1/2 yt p lambda q1 p lambda y. And this goes to -1/2 trace p lambda qk plus 1/2 yt p lambda qk p lambda y. So this is the gradient. So I plus 1. And this is then always with the I here. And this needs to be pre-multiplied by the Hessian matrix, which is, this. So, yeah. So, did I go completely mental and tell you about stuff that never happens anywhere and stuff? So, just to show you that this is actually not the case, let us have a brief look from where this is coming from, because I'm not doing this for fun. Yes?
Is there an easy way to interpret the matrix P lambda? So what do those?
Yeah, there is actually, there is an interpretation. Actually, I can show you that, but it's not easy to give you that because it rests on the Bayesian way of looking at things. So let me show you two things. So the last step here was not really nice, but it really requires a lot of writing up. And I want to show you at least where this is coming from and why it plays a role. So and then also answer this question in this context. So first of all, this is of course, as I showed you previously, what is going on in SPN Ramel. Where these things are implemented. So roughly look at this thing and look at these things, which have these P and Q matrices in it. Yeah. So of course there's more code that does a specific thing, but this is where this is implemented with some little adjustments here and there, but essentially that's it. And also let me show you the corresponding papers where you actually see the equations that I've just shown you. Just where I have them best. Do I have them somewhere? Here, no, so we need to go online. So there was this major update of SPM in the early 2000s, where all these things were put into SPM, and there are unfortunately not many papers about this, and the papers that exist are not the most clear, interesting, papers ever. Nevertheless, they exist, and I just want to show you them. Interesting. Interesting. So this is this classical and Bayesian inference in new imaging theory is the paper that introduces the Ramel approach in the context of expectation maximization, which we actually don't discuss. And the equations that we've just seen are here. So we here have our Ramel objective function. So this Ramel objective stuff, that's already from the late 70s. So the only thing that happened there is that essentially Kai Friston adapted the state-of-the-art statistics of the late 70s, so late 70s, to fMRI data, like 20 years later, and we are now talking about this 20 years later. And this here has the gradient that we've just seen, and it has this expected Hessian, and this P matrix, which you also see here, that's from a Bayesian perspective, that's the conditional covariance matrix of the conditional covariance matrix of what? I'm not quite able to explain this right now, because it's you need to view this whole thing then from a Bayesian setting, and then you do inference for, I think, the beta parameters, and then this is the covariance matrix of the beta parameters. But because the beta parameters are out anyway, and so on, it doesn't really make sense right now. And there is another story, so that you can give a completely different story to Ramel, which is looking at Ramel in a Bayesian setting. And this is actually what we did in this paper with Ludger Starke a couple of years ago, where you start from a whole different setup, where you have priors over the beta parameters and over the covariance parameters, and then you can derive the Ramel objective function under a specific a prior setting and variational distribution over beta. So there's a different story to Ramel that we didn't discuss, and there I think it's easier to give a clear motivation for this P matrix. So that's one occasion where they show up. They show up a little bit clearer actually in the Friston paper on posterior probability maps. So that's when they tried to do some Bayesian inference for the GLM, which never really started. So here you can see this a little bit better. So yeah, so it's the it's here. So here are the Ramel equations again, and so this is the conditional covariance matrix, and this is maybe a rewrite of that. So yeah, currently I just have this P matrix as a definition, which allows then to have this K matrix rewritten. So what we've just seen is also written up here, but of course without any explanation, like always in these Carl papers. But so we've now given an explanation starting from Newton-Raphson and the Ramel log likelihood function. And there was one last thing that I wanted to show you. So this is this Ramel we've seen there. Yeah, the Bayesian story is I don't get quite clear right now. No. But essentially that is that. So this is not quite nice, but so these are the components of the gradient. So you have to stack them together in a vector, and these are the components of the Hessian matrix, or these of the Hessian matrix. So you have to arrange them properly in a matrix. So now we'll not be able to do that now, but you have here a K by K matrix, where at the IJ location you have the trace of P lambda and then J and I in the matrix, and the gradient we brought up here. Yeah, so that's Ramel. From Ramel you get an estimate for lambda, and then this lambda estimate you can use to estimate beta. And the good thing about Ramel is, although we haven't really shown that, because for this, to really show this, we actually need also the expectation maximization approach, we have an unbiased estimate of the variance parameter. So it's it's basically how far statistics went in terms of estimating GLMs with non-spherical covariance matrices by the late 70s, after like 100 years of doing this, and how this was then brought into new imaging in the early 2000s. And since then it's there, everybody runs it. Ramel iteration 1, Ramel iteration 2, and it doesn't hurt to know about it. But the bottom line is non-spherical covariance matrices and the aim of having an unbiased estimator or unbiased estimates of the covariance parameters, these lambdas. Yeah?
I was wondering, in this context, in what ways Bayesian statistics can be more advantageous than numerical statistics?
Well, in no way. The reason I'm talking here mainly about the frequentist approach is because everybody's using the frequentist approach, and we will also, when we talk about inference later on, we will also look at the random field theory from the frequentist perspective. Actually, when we talk here about Ramel estimation, you can view Ramel estimation both as a frequentist approach and as a Bayesian approach. So if you want to know how to look at Ramel from the Bayesian approach, have a look at our paper from 2017 with Ludger Starke on variational inference for general linear models. So the Ramel specifics can be interpreted both under a Bayesian model where you have priors over the parameters, or here from the frequentist perspective where you want to remove the contribution of these fixed effects. So Ramel is kind of happening both in the frequentist and Bayesian scenario. General Bayes is a little bit nicer if you have good reasons to incorporate some prior information. The thing is, fMRI data analysis using GLMs with the convolution of onset function, nobody does that in a Bayesian manner. So it's not really worthwhile talking about it because nobody does it anyway, because everybody's doing what's implemented. I mean, Bayesian is there is an implementation, so you can click Bayesian estimation of GLMs and SVMs. This then uses some variational Bayes for autoregressive models that will penny implemented. However, this is really not being used. Okay, so this now we got quite far into the details of estimating the GLM. So after Christmas, we will take a step back and first look at the whole picture again of first level fMRI data analysis, and then introduce stochastic processes to understand why we have these covariance components, especially those, and then to understand how now we've been looking always at estimating one voxel, but now then we want to also give p-values to voxel activations in space and make sure that we do the testing in a multiple comparison corrected manner. So that's the big topic for January. Basically, stochastic processes for covariance components and for random field theory based inference. Well, and then we're done with the classical stuff, and in the summer term we do machine learning, because everybody wants to do machine learning. Machine learning, as I call it, bad statistics. Good. Then I would stop here. Merry Christmas and stuff, but we will meet again tonight and on Friday, and we won't, I guess. No one of you, neither of you.
Tonight, but not on Friday.
Okay. Yep. Good. Then see you tonight. Happy New Year. Good. So today I want to first review everything that we did already in terms of GLM analysis of fMRI data, to somehow get started again, and also to basically set up what the remainder of the term will be about, because certain parts, especially with the introduction of random fields and family wise error rates in multiple testing and so on, they will get a little bit more involved, and it's good to, before going into the mathematical details of things, to review the intuition and where we are at overall. So the first thing, and that will be basically, I guess the first hour will be a review of what we've seen so far, because we've done quite a lot, and in the end, when we talked about Ramel, again, I can think that things get a little bit lost in the details. So I first want to, give an overview again where we are. So it's GLM for FMI. Obviously, that's what we've been doing since October, and what we are so far basically mainly concerned with. Although, of course, things like maximum likelihood estimation and GLMs, they are general approaches, but what we've really been thinking of most of the time is the fMRI data, so the MR signal from a single participant in a single run. And for a single voxel. So this is what the data that we've been talking about all the time, and for which we set up a GLM model. Yeah? So a series of, 400 data points that go up and down and represent data from a single voxel, so a single 3D location in the brain, from a single run when the participant did an experiment, and a single participant. Yeah, so that's the data that we've been mainly interested in all the time. And for this data, we formulated a model. So the first big thing that we discussed, of course, in our trials of model formulation, model estimation, and model evaluation was model formulation. And the model that we formulated was, of course, the GLM. So we first looked at the GLM formulation in its typical form, where you have a data vector y, which is given by a design matrix times some parameters plus some error components, and these error components, or this error vector, is distributed according to a multivariate Gaussian and has a spherical covariance matrix, by which I mean this diagonal covariance matrix that is given by the multiple of our variance parameter with the identity matrix. Then we, of course, also discussed that this can be equivalently be expressed as a probability density function over the data. That is, of course, again a multivariate normal distribution or Gaussian distribution with expectation parameter given by the design matrix times the beta parameter, and with covariance matrix parameter given by the covariance matrix of the error, which just follows from the linear Gaussian transformation theory. So that was basically how we started the sessions in October, and then we quickly moved on to GLM for fMRI, where this GLM now takes the form of a multiple linear regression, and the important thing is that the columns of the design matrix, so which I now write here as x1, x2, and so these are supposed to be vectors, where these columns of the design matrix represent the hemodynamic response function convolved condition onset functions. Yeah? So we spent some time to discuss how onset functions are convolved with the HRF and how this is a sensible approach under the assumption that the stimulus neural system bold response
MR signal system is a linear time invariant model, and how these regressors are then formed, and that the associated beta parameters can be interpreted as the condition effects. We looked at these examples from different voxels that respond differently, and how their responses are then encoded in the, if you want, true but unknown beta parameters, and then of course also the estimated parameters. So when we talked about this, this is where we had this relatively long session on convolution, where the regressors for a specific time point I were formed by this convolution sum over the entries of the hemodynamic response function at time point 0 multiplied with the onset functions. In the actual text, the regressors are called YE because they're thought of as data there, or as the transformed sequence, and the X is the input sequence. Don't get confused there. So these things that come out of the convolution in FMI, they are the entries. They are the columns of the design matrix. And we've also, for completeness here, we also looked at the hemodynamic response function. So that was given by this difference of two gamma probability densities. If you remember in the script, so this then looked roughly like this. So it takes discrete inputs and then maps these discrete inputs to the difference of two gamma densities, where these densities have nothing to do with I'm just writing out the formula here, where these densities have nothing to do with probability theory. They just are used to create this analytical model of the hemodynamic response function. So everything that this thing here is doing that I'm currently writing up is to give you a function that looks like a hemodynamic response function that looks essentially like this. Yeah. So that's this double gamma, as it's often colloquially referred to, double gamma HF. And again, all of this to create the regressors of the design matrix. And this G function, G is the gamma density function. So that was our model formulation. Maybe to unfortunately, I forgot my mouse. So I can use this to remind you of what this means in practice. To remind you what this means in practice is essentially to formulate, to put in the things into, especially the onset functions, into the respective mask in the, for example, the SPM software. It's the same thing if you use FSL for data analysis. And then what you end up with is, after clicking something like run, you create the design matrix, which you then can inspect, and this is what I want to show you. So, initialize here. Itself in this SPM structure, and you get this design matrix, which you can have a look at, and that's essentially it. So this is the formulation where we needed to, where we basically went via the specified first level, so meaning participant analysis, and had to fill in things like the timing parameters, and which basis functions, for example here the canonical HF, so which convolution function, and which onsets, which data we used. That's not really for the model, but which onsets we used. So this was all of this, and what came out was essentially the design matrix. What also comes out, and we will get to that in a second, is the covariance matrix, but we will see that in a second again. So that was basically the model formulation step, and once we had this in place, we then went to the next step in the model formulation, model estimation, model evaluation procedure, which is a fairly typical thing for probabilistic models, namely to do maximum likelihood estimation. And for maximum likelihood estimation, we first formulated the log likelihood function, which in general is a function from the parameter space to the real numbers, takes a parameter as input, maps it onto the value of the log likelihood function, which is defined as the log of the likelihood, and the likelihood just being defined as the probability of the data under the model with the specific parameters. Yeah, and because we had formulated this previously, so that was our normal distribution over the data, we basically already had our log likelihood function, and then we used the idea of maximum likelihood to choose that parameter estimate, which maximizes the log likelihood function over parameter space. And when we did this, what we ended up with were for our model here, when we applied this to our general linear model, what we ended up with were the beta maximum likelihood estimator, which is a transformation of the data by essentially the design matrix multiplied by itself, inverted, and then transposed, applied to the data. And we also ended up with the the maximum likelihood estimator for the variance parameter, which is given, on which we derived there, assuming that we know that we have the beta parameter estimate, which is given by the residual errors. So the prediction error between the real data and the predicted data based on the maximum likelihood estimator squared and summed up, divided by n. And then I already mentioned when we did this that this is not an unbiased estimator, and that an unbiased estimator is given if we don't divide only by n but by n minus p, which is then also usually called the sample variance estimator. And we later then also discussed that this is actually the Ramel estimate, although I did not really show, and will also not show in this year, that you get to this formula with the n minus p when you apply the Ramel framework, because to do that, what you need to do is actually to do expectation maximization, and we don't discuss the expectation maximization algorithm in this year. So if you really want to know where the minus p is coming from, then have a look at the book at one point, or try to Google it. It's actually not that easy to find where this is coming from. Anyway, so this is what we did for model estimation on a first pass, where we dealt the whole time with spherical error
covariance matrices. And based on this, we then went into model evaluation the first time to basically introduce t-statistics, and t-statistics based on the distributions of the beta parameter estimator distribution, which we established with the linear Gaussian transformation theorem to be also normally distributed, unbiased, so the expectation parameter is the true but unknown value, and with this covariance matrix. And similarly, if a little bit less formal, we introduced the distribution of the scaled Ramel or sample variance parameter estimate, which was given by a chi-square distribution, mainly because here these normal distributed things are squared, so they cannot be again normally distributed, but will always be positive, so they don't have a normal distribution, but they have a chi-square distribution with n minus p degrees of freedom as parameters. So based on these estimate distributions, we then introduced the t-statistic. So we then came to the t-statistic, which for a given contrast weight vector c was given by this ratio of the difference between the estimated parameters and some hypothesized parameter values, for example 0, if you do a t-test against 0. So this effect size or effect measure divided by the measure of the variance. So that the basic intuition of a t-value is that it's how strong the effect is compared to an estimate of the variance of the effect. The nice thing about the t-statistic, in addition, because it's basically formulated in terms of this thing, so the beta parameter estimate and the variance parameter estimate, and the distributions of these are known, and then you combine these distributions, this thing then being distributed according to a t distribution with n minus p degrees of freedom. And we've also looked in some details into this. And basically then ended up there when we did our first pass-through model evaluation with the idea that we now have this univariate outcome of some parameter contrast. So for example, if you have two conditions, beta 1 and beta 2 in your design, and you want to know whether there's a significant difference between them, that you use a contrast vector of the form -1 and 1, and then you basically can test whether the difference, if we have it this way around, then we have beta 2 minus beta 1 equal or not equal to 0. Then based on observed t-statistic, with so far the main intuition that if the t-statistic is quite large under this null model, that the null hypothesis that the contrast, so this product of the contrast weight vector with the beta parameter is 0, is unlikely. And in the remainder of this term, we want to go a lot more into detail about this idea of statistical testing. So for now, we've only established that there is something like a t-statistic, that it has a given distribution, but we have not really formalized what a test is. We also haven't talked about this thing that we are not only testing this at a single voxel, because so far we've only talked about the single voxel, but we test these hypotheses at all voxel locations in the brain, which then induces a multiple testing scenario.
And a big part of fMRI data analysis, statistical analysis, is then how to account for this multiple testing problem. And the standard approach that is implemented in all the softwares is random field theory, based p-value evaluation or random field theory. And this is going to be a big topic then for the remainder. So this was our first pass into model evaluation, but then we went back to model estimation and also model formulation in a way, because we introduced this idea that not everything that is happening in the data is accounted for in the design matrix, and we introduced this idea of error correlations. And with error correlations, we basically then went from the idea of a spherical covariance matrix, so from the sigma square IN as the covariance matrix of the errors. I can write like this, maybe the other way around. That's more intuitive. So we went from assuming that there's no correlation between the errors to the idea that there might be correlation between the errors, and the question of what to do then. And this, of course, meant that we changed the model, the formulated model. We also seen that if we would now proceed with all the equations and the t-distribution as is, that we would be misled to get false positives, because our t-values will be in general too high compared to the analytical distribution. So we basically needed to go back to the whiteboard and or blackboard and think again. And there we discussed two cases. The first case that we know the error correlation structure, so that we have precise knowledge of it. So we don't have a free parameter in this case. Maybe we have a scaling parameter, but in general we have a full knowledge of the error correlation structure. And in this context, we introduced generalized least squares estimation and data whitening, where the basic idea was that, well, if we, and the main idea in terms of data whitening was, if we know, if we have a GLM of this form, and we know V, and we also know that it's not the spherical error covariance matrix, which would allow us to just use standard inference in terms of the t-distribution. That what we can do is to whiten the data and do inference on this whitened data, where the main idea was to first decompose the V matrix into its square root, if you want, to define a whitening matrix as the inverse of K, and then apply this to our non-white GLM. So this is what we discussed when we discussed generalized least squares estimation, where we start like this. So we have a non-spherical GLM, or a GLM with non-spherical errors. Then we multiply this whole thing with our whitening matrix. And then we get this new GLM, which is the multiplied GLM just written up again so that it looks like a normal GLM. And the main thing here being that due to this definition of the whitening matrix and the fact how covariance matrices transform under multiplication, we get to a spherical GLM again. So we get again here, and this means we can use standard t-test again, or standard t-inference. Now, this was of course under the assumption that we know this variance matrix, and of course that's not really realistic, because that's also part of the model and not directly observed. What we observe is the data and not its covariance matrix. So this is why we then, and this was the last thing that we did before Christmas, if this covariance matrix of the area is not known, we went into this business of covariance component estimation, which was then combined with Ramel. So this was then the thing that we did before Christmas. And here the main thing is that the error covariance matrix is not known. So what we did then is to say, okay, it's not known, so let's model it, and we model it as a sum of covariance components, where if you read the literature, it's not quite clear what these covariance components are. So what I called things are here these covariance component parameters, which we actually estimate using Ramel, and the covariance component basis matrices. And if you just hear the term covariance components, it's not necessarily completely clear whether these matrices are meant or whether these parameters are meant. And so basically we imposed some structure on the error covariances, and then used Ramel in its Fischer Scoring implementation to estimate these. And this I'm not writing out again. This was basically what we did in the last hours before Christmas. Estimate with Ramel Fischer Scoring, for which we needed to basically, to understand what Fischer Scoring is, we needed to understand what Newton-Raphson estimation is, and what the Fischer information matrices are. And once we have estimated these values, so once we have our estimates for these lambda k, then, and this is actually how it's done in the SPM software, then these are pooled over voxels. And we get an estimate of the error covariance matrix, which is then just given by these estimates derived from this Ramel algorithm multiplied by Qi, and then they are treated as known, and we can do data whitening. So then we basically go back here. And then for every voxel we treat the error covariance as if it was known, because we've estimated from really many voxels, and can use again the t-distribution for inference. So this is essentially what we've done from October to Christmas. Again, from the practical perspective, what this amounts to is the formulation of the GLM, also in terms of the covariances, this thing with the covariance component or basis matrices, where the first one is the identity matrix and the second one is this exponential of the difference between time points, which I introduced but so far haven't justified, and will only be able to justify once we talked about random processes and random fields. Where this is showing up is in this serial correlation. This is very weird, but this is where this is showing up. If you decide for AR1, this is where you set up the covariance matrix structure and then lead this whole thing into in a GLM with non-spherical covariance matrix and then induce Ramel estimation. This whole estimation business, then once everything is formulated, happens fairly easily by clicking estimate and overwrite. And then what SPM tells you is that it's estimating the non-sphericity, and this non-sphericity, because it's Carl, applies to two things. It's the temporal non-sphericity, which is the non-sphericity of the errors, and later on it also estimates so here's where it's estimating the temporal non-sphericity using Ramel, and then at a later time point, actually at this time point here, it's also estimating the spatial non-sphericity, which is part of the random field business, which we haven't discussed yet. So there's one function that does both sphericity estimations, and then at one point, fairly quickly actually, it's estimated over the whole thing. So spatial non-sphericities, which we haven't discussed yet, and then the model is estimated. And so this is everything that we've done so far, which is quite a lot. But so far, obviously, you don't see any blobs in the brain, so nothing. The results are not really there. And the results then relate to what we want to do in the remainder. So let me first tell you what we are now going to do until mid-February. And as the last part of this classical, of this GLM-based fMRI analysis, before in the summer term we go to the machine learning analysis of fMRI data or new imaging data. So the remaining things to discuss this term are now that we have evaluated parameter estimates of the GLM for each voxel, and we have ensured that the t statistics that we can form on these parameter estimates, so on the beta and the variance parameter estimates, these t statistics are actually t distributed because we have accounted for temporal autocorrelations using whitening. Then we now want to do formal statistical testing, so to decide essentially whether for each voxel there is actually activation or not. So the first thing we want to discuss is statistical testing. So what does it actually mean to do statistical testing? And then, of course, with fMRI data, we have not only a single voxel, as we've treated everything so far, but the estimation already happened for all the voxels, but one after the other. So it's essentially talking about the estimation in one voxel. But now when we evaluate the t-tests and then look at a statistical parametric map where we have all these statistics together, then we need to account for this multiple testing problem, and we have to discuss what that means and what it means to control the family-wise error rate in general. So that will be the first thing, and this is also in the next hour with which I want to start. And then the next thing, after we discuss what statistical testing actually means, we will discuss the approach that is used in neuroimaging to deal with the multiple testing problem, which is based on random field theory. So for this we have to introduce the idea of random fields and how they are used for family-wise error rate correction or for multiple testing control in neuroimaging. So this will be the main thing to discuss until February. One thing that I hope to put in at one point is, once we know what a random field is, and when we know what a random field is, we also know what a random process is, because it's a special random field, that at one point I can give you the account of why this autocorrelation function in the first level has the form that it has, because this can only be motivated based on random processes. So this is referring to this second basis function in, I think it was that, yeah, it was different, it doesn't really matter, so I think it was Q2 was ZT or something, which had this exponential in the difference between I minus j or something like this, where this is coming from. So this has to do with stochastic processes or random processes, and this we can sneak in. But so this, now I talk more about this. The most important and the biggest chunk that we're going to discuss is definitely this. This is what we do first, and at one point I will sneak that in, because we can then, once we know what a random field is, understand what's going on there. So in terms of the practical aspects of fMRI analysis, this is of course all model evaluation or parameter inference based on the model. And what this really relates to is what you do when you do the following. You've now estimated a GLM, and then you want to look at the results. And of course you need to define a contrast. So here we have three beta parameters: beta 1, beta 2, beta 3 for each of the columns of the design matrix. And I'm now interested in whether the beta parameter for this first column, which were, if you remember, these were checkerboards that were shown at specific times to a participant, and these were also checkerboards but of lower contrast, whether the sum of these two betas is larger than 0. So I define a new contrast where I want beta 1 plus beta 2. So I take the contrast weight vector 1, 1, and from this get the contrast beta 1 plus beta 2 larger or unequal to 0. And now I test this for all the voxels in the brain by clicking OK. And this is just specifying the contrast weight, and then basically saying that I want to evaluate this contrast in terms of t values all over the brain. And then I have to, in fMRI data analysis, do a little bit more, because this then relates to the random field theory business. Masking is not that important. What is important is that I have to define, and this is what I'm doing with these two clicks here, I have to define a cluster defining threshold, which is just, so if you think there's this SPM with all the t values now, because I specified a contrast, so each voxel has a t value now, as you also remember from this first lecture on mass univariate fMRI. Now I'm thresholding this map, so this brain map at a given value. So the t values, they range between -10, let's say, and +10, and I'm obviously interested in the ones that are very positive, so I'm thresholding it at around 4. This is done via p values, but we can actually define a t value, I think. So let's threshold it at 4. And if I want to do a certain kind of test which relates to set levels, I can also give a voxel threshold. Again, this is part of the random field theory business that we need to discuss. And then once I've done that, I end up with this map and this table. And it's essentially this table that in terms of random field theory we need to discuss. Because this table has 3 levels of inference: peak level, cluster level, and set level. And the question is, what does that mean? It has the t-value at a given voxel here. That's something we can understand already, because this now has a t-value. It's the beta 1 plus beta 2 divided by the variance. Has a high t-value here. But then it also has p-values associated with it, which are uncorrected and family-wise error corrected, and we don't know what that means yet, what that means, or what these values mean. Then it has something called cluster level, and what you mostly find in fMRI publications is that people report family-wise error corrected inference at the cluster level. So what they do is they look into this table and select the clusters and report them that have a p-value smaller than 0.005 in this column here, because that usually gives you more things to report. What this means we also don't know, because it relates to the random field theory framework, and then the set level, which we also don't know what that means. Here you can see that the threshold was chosen as 4. Here some expected voxels per clusters, numbers of clusters, and so on, full width, half maximum. All these things are things that relate to the random field theory business, which we now want to basically discuss. And what you also can do if you like to do things like that, you can of course put things on, put this map on, overlay it on some anatomical image, and then you see some blobs on the brain. But these are of course just these clustered and rendered onto an anatomical image, and the result of a fMRI study is not an image like this, but it's the table. And what this table means, which is the end result of classical fMRI analysis, this is basically the topic for the next 6 weeks. Yeah? Questions after this monologue?
I have several questions. I will share about, but there is only time for all of them now. Should I start after we are taking a break?
So what are your questions?
For example, there are at least 7 or 8 questions. What make of the general ones regarding the script? There are some things in the script that you didn't discuss in the lecture. What these things have also corresponding study questions.
Okay, so that's a question about the exam. So what I've been, what I did already is have a look at the script again, because I took out certain parts that I didn't discuss. So, for example, there was something on design matrices and orthogonal, non-orthogonal stuff. I took out these things, so this is what I'm taking care of. So you don't have to worry about this.
So what is relevant to the exam is only what you discussed?
Yes.
Okay. And in the script, there are that chapter on restricted maximum likelihood estimation, there are no study questions for this chapter. Will you add something later for the example?
There are no questions, there you say? Yes. So far, I think because this was kind of a novel section, there will be 5 questions for that. Yeah. Don't worry about the exam. We'll be fine.
Should I start with the questions regarding the content?
Yeah.
For example, from the very first chapter, there was something about sampling 400 data points, and with data points to be following measured bulk measures from the fMRI, 400 for one voxel. So this would mean a 400-dimensional sample from 400-dimensional Gaussian. And it's also mentioned that this is equivalent to 400 random data points from a one-dimensional Gaussian distribution. How would we conceptualize this if you wanted to sample so 100 data points for several voxels?
No, we don't. So that's the point.
Okay.
So, I mean, one can generalize multivariate Gaussians to how they call it? They have a different name. It's about sampling matrices. So basically sampling Gaussian matrices, but we don't. So this is the whole point of this mass univariate approach that we did so far, that we only sample multivariate Gaussians and voxel by voxel. What will happen now when we talk about random field theory is that we actually stop thinking about the 400 data points from a single voxel, but now we've collapsed things, as you can also see here. We collapse things to t-values, and what we will now talk about is a field of t-values. So we talk about t-values being sampled over space. So this is when we now go into the spatial domain. We view what we've done so far as a computational simplification and create basically a new model, or a model that we had in mind all the time, but we basically evaluated computationally efficient. We have this new model of a field, so a spatially extended random process of t statistics, or z statistics, as we will see.
Yeah. Okay. And regarding the GLM and the method in general, I wondered why one doesn't simply average voxels for a hypothesized region of interest, like one does, for example, in psychometrics, where one averages several questions that are called to represent one construct.
Yeah, one can do a region of interest analysis. The thing is, in general, so in terms of brain mapping, and the question is what you then want to do. I mean, you have if you have a region of interest, you would have to have a good story why you are now interested in that. For visual cortex, you usually have that, so that makes sense. But the more general question that is answered by brain mapping is the brain does a task, which areas in the brain are involved in that task, and then because you measure the whole brain, then why not evaluate the whole brain? And this is why region of interest analysis are done mainly in the vision science, because people there only look at the visual cortex. The other thing is, if you acquire that much data and then you throw away most of the data, and the question is why you first acquired it. So, yeah.
For example, in one example, when we compared two regions and their activation, when we formalized the GLM model, there we hypothesized that one voxel belonged to a certain region and the other one the other region, and we hypothesized different activations. Why wouldn't we? And here we had some hypotheses about the regions. Why not simply average the several voxels belonging to each region and then compare them directly?
No, well, so the thing with averaging about regions is, first of all, there is some sort of averaging over regions in the smoothing step of the pre-processing. So the regions that you can detect, of course, based on this match filter theorem, they somehow have to have the size of the things that you are later looking at under the smoothing constraints that you also need for random field theory. The other thing is, per se, you don't know what are functionally relevant distinct regions. So, I mean, of course, you can have some anatomical constraints, but there's, of course, no guarantee that this is also functionally interpretable. And that's the main thing. And the other thing is, of course, once you have the result, and this was also the result with these two voxels there, once you have something like a map like this, of course, you can do regional inferences. And this is the main point, of course, that you, for example, say, okay, here there was in this very simple example, there was left visual hemifield checkerboard stimulation, and now primarily right visual cortex is active. So then, of course, you say, okay, the right visual cortex is more more active than the left visual cortex. I mean, you do these kind of regional inferences, but if you always want to average, you would have to have a good parcellation scheme for the brain in the first place. And if you try to figure out what are the functionally relevant regions, you don't have that before, so you need to go via the entire voxel set.
Yeah. And in undergraduate statistics, we always had normal distribution as an assumption for right test, for no-validity test. In our conceptualization, this is equivalent to spherical covariance matrices, right?
No, normal distribution is just Gaussian distribution, and if you in undergraduate statistics had independent and identically distributed data from normal distributions, that would be equivalent to a multivariate normally distributed data with a spherical covariance matrix.
The assumption was that the dependent variable should be Gaussian, the normally distributed. Is this equivalent to...
No, this is what they always say in undergrad statistics, but this is a misunderstanding. So in undergrad statistics, what they mean is that the errors are normally distributed. But they often say that based on this, it's somewhat equivalent, but the independence is in the errors and not in the data points, and this is the important difference. So if you look at this here, here the errors are Gaussian distributed, and the data are also Gaussian distributed or normally distributed. The errors are identically and independently distributed. They are identically distributed because they're all centered on 0, and they are independent because they come from this covariance matrix. The data, they are not identically distributed because in each entry of the expectation vector there you have this product of the corresponding row of the design matrix with the beta parameters, and because the design matrix changes, also the entry in the expectation vector changes. So, which also means that if you analyze just the data per se, because there is dependency, for example, between adjacent data points based on this mean shift, that the data points are not independent. So this is a misconception in undergraduate psychology statistics, that people always say that the data are normally distributed, or they are normally distributed, but the important thing is this, the errors are normally and independently distributed. This is the important thing.
And we wanted to take the MRI signal not as a dependent variable, but as an independent variable. So here we would have an independent variable that isn't really deterministic for like conditions. Would we have to define error terms for the independent variable?
Now what this relates to is, so if you want to do that, so if you want to correlate one voxel's time course with another voxel time course, you are in the business of correlation and not regression, and the idea in correlation is that both your dependent and your independent variable are random variables, and hence you look at bivariate distributions and you look at correlations. We didn't discuss that at all. One thing that is often done is that the subtlety is somewhat neglected, and for example, if you do things like psychophysiological interaction analysis, so PPI analysis, you use voxel time series also in the GLM. And of course, simple linear regression and correlation are really, really closely related, but the interpretation of the independent variable is different. I didn't discuss the difference between simple linear regression and correlation here, so that can be done. One sees a lot of similarities in terms of the formulas that come out, which also means that correlation is a measure of linear dependence. But as you say, in regression and in the GLM, the independent variable is not a random variable, but it's deterministic. And here it's of course always deterministic because you choose how it is because it's your experimental design.
In the Maximum estimation, when we estimate the beta parameter, is this beta parameter equivalent to the beta weight in regression analysis?
Yeah, sure.
Okay. And how do we come to the intercept? Because we didn't.
The intercept, so if you think about simple linear regression, So in the very beginning, we discussed simple linear regression, where in the design matrix we had a column of ones and a column of the values of the independent variable. Of course, there we had two beta parameters, one beta parameter related to the independent variable and one beta parameter related to this column of ones. And this column of ones, of course, adds 1 times this beta parameter to every data point and then reflects the intercept. So the intercept, you also see that here in the design matrix. Here, this is a column of only ones, so this is modeling the offset.
Okay. Yeah, and also we had in regression analysis and regression statistics, we had standardized vector weights and normal vector weights. Is this something?
The
standardized vector weights were also equivalent to the correlation between the dependent and independent variables we usually have.
Yeah, this relates to this is not really important here, but this this is about this how to relate simple linear regression to correlation. So I think so we are not discussing that here, but this makes some sense because correlation and simple linear regression are essentially the same thing, but you need to adjust the parameters, which then will relate to this, what you just said.
Okay. But yeah, what we talked about, what we estimated with the maximum estimation is non-standardized.
It's just the beta parameters of a GL.
Yeah. Regarding the t-statistics, you define it as a measure of the effect divided by the variance, but the t-statistics is usually divided by the standard error, right? No? It's the standard deviation?
It's the t-statistic is I know what you mean. So sometimes you see this formula for the t-statistic where the standard error of mean plays a role. But this is already, so this is, now there I would suggest that you read closely the script, because this relationship between this formula and this classical formula of a t, like you know it from undergrad statistics, of a one simple t-test t-statistic, this is explicitly in the script, and essentially where this division by n comes in, which then, so when you relate the sample variance, so here you have this sample variance, then you have the square root of it, so you have the simple standard deviation, and then you divide, for the standard error of mean, you divide by the number of data points, the square root of the number of data points. This is in this term, but this is written up all in the script, so have a close read there.
I read it, and here we find, for example, t-statistics is a measure of the effect size associated with the J independent experimental variable measured relative to the data variability. But you also said in the lecture that relative to the data variability and the sample size, the sample size has an effect on, in contrast to the Cohen's d, for example.
Yeah.
But you describe it as annoying. But do you see it only as annoying, and do you see it as a mathematician? Don't you think that its effect, for example, when comparing t values from different studies that have different sample sizes, don't you find that? Don't you think that it would be better to compare Cohen's d's between studies?
I think what I find, I don't know what I find annoying, but I find a lot of things annoying. But what I always, so in psychology statistics, there's a big fuss about Cohen's d, and Cohen's d is just a transformation of t-statistics. So t-statistics and Cohen's d are equivalent. If you know the sample size, then you can transform one into the other. So, So there's no magic, and so t-statistics are fine. T-statistics are measures of effect versus variance as Cohen's d. The only difference is that t is dependent on the number of data points, but of course the number of data points is related to the variability. So more data points, less variability. Yeah. So let's not discuss that further, please, because there's nothing in there. There's nothing to discuss.
But I mean, when there are meta-analyses for it from our
Yeah, sure.
Do do they usually use these statistics when computing the
I don't know what they
results?
They will have their methods to do proper meta-analysis. We would have to look into them. I'm not an expert on meta-analysis.
Yeah. Okay. I have a specific question to the graphic and the script, which you also.
So how many more questions do you have? Because I think we have to stop now.
Yeah.
So I would suggest that you come to the lecture in the morning and ask your questions here. No, not these questions, but questions that you have. So you come here and that you read things and that we can discuss that here because it's useful. So I like the questions because it helps to clarify things, but it's would make more sense if you would come weekly and ask a couple of questions. Yeah? Good. So there's one more question.
Yeah, regarding this does the spatial resolution of our MI data affect the probability to get a significant effect in terms of t-test? Or how does it?
Yeah. So yes, this is then, of course, the topic of random field theory. So the t-statistics that we evaluate in a given voxel, they just depend on the data in a given voxel and also remain constant. But if you now want to evaluate the statistical significance, you first need to know what statistical significance means and how essentially this is evaluated in FMI. And this is in the random field theory business. It then depends essentially on the physical search space, so how many voxels there are, and on the smoothness of the random field. But this is all stuff that we're going to discuss now. Yeah? Good. Then let's have a break now and then do half an hour of statistical testing from 9:15 to 9:45.